not live yet. Bonjour, mesdames et messieurs, chers amis, chers collègues, chers spectateurs en France. Je vous souhaite la bienvenue à tous. C'est un grand plaisir de voir autant de personnes réunies aujourd'hui. Auch ein herzliches Willkommen an unsere deutschen Teilnehmer, Freunde und Kollegen. Es freut mich, dass so viele unserer Einladung folgen konnten und heute und morgen hier mit von der Partie sind. My name is Daniel Kremers, and on behalf of my colleague Jean Ponce and myself, I'd like to welcome you to the French-German Machine Learning Symposium. Machine learning is revolutionizing our world and has an increasing impact on virtually all areas of science, technological development, and society at large. Countries around the globe are investing increasing amounts of effort into building expertise and competence in this area. Examples include, on the French side, the Centre 3A, and on the German side, the National Competence Centers for Machine Learning. The aim of this symposium is to bring together some of the leading experts in this field from both countries and ask them to offer us a glimpse into their research to exchange perspectives on machine learning developments and to thereby foster stronger ties and possibly collaborations between the two countries. Our symposium merely features a small subset of all the strong researchers in this area, both in France and in Germany. And so we apologize to all those that we were not able to include this time around. The symposium has actually been 2 years in the making. It was originally planned to be held physically here in Munich in May of last year, but due to the pandemic, we had to move it several times, and so I appreciate the patience of all our speakers. And ultimately, we decided to now hold it in this purely virtual format. I apologize as we cannot demonstrate the usual Bavarian hospitality now, but I promise to make up for this. Once the pandemic is over, we would be happy to do a real physical follow-up event with beer and pretzels here in Munich next year. Yet to provide this symposium with a Bavarian element, it is my great pleasure to now hand over to the Minister President of the Free State of Bavaria, Markus Söder, for a short opening statement.
Ein herzliches Grüß Gott und ein herzliches Willkommen zu dieser Form der Zusammenarbeit, die über ein ganz besonderes Thema stattfindet. Die deutsch-französische Kooperation ist auf allen politischen Ebenen wichtig, aber ganz besonders, wenn es um Technologie geht. Wir stehen in einem internationalen Wettbewerb mit Partnern und Freunden aus den USA, aber auch Wettbewerbern aus China um die Zukunft der Intelligenz. Und künstliche Intelligenz spielt dabei die entscheidende Rolle. Klar ist, wer die Produkte und Wertschöpfung der Zukunft gestalten will, der muss auf der einen Seite auch tatsächlich technologisch voranschreitend und muss zweitens dazu aber eine Kultur von Forschung und Entwicklung haben, die dazu passt. Wir gehen voran. Bayern ist in Deutschland das führende Land für künstliche Intelligenz. Mit unserer Hightech-Agenda, in der wir insgesamt 3,5 Milliarden Euro auf den Tisch legen, schaffen wir es am Ende über 1000 Professuren über alle Bereiche der Naturwissenschaften auf den Weg zu bringen und dabei allein 100 Professuren für künstliche Intelligenz. Bayern schafft in den nächsten 2 Jahren für KI genauso viele Lehrstühle, wie Deutschland in den nächsten 4 Jahren macht. Wir wollen zum führenden Land der künstlichen Intelligenz werden. Ganz Bayern wird ein moderner KI-District. Hinzu kommt, dass wir mit der Investition und Entwicklung in die Quantencomputing, in der Ergänzung Quantencomputing und künstliche Intelligenz ehrlich in eine neue Dimension kommen. Das ist, wie man es im Star Trek-Universum sagen würde, der Warp-Antrieb für künstliches und auch intelligentes Rechnen. Dies wird uns Möglichkeiten schaffen, von denen wir heute noch gar nicht ahnen. Unsere stärksten Wettbewerber investieren bereits. Und um auf Augenhöhe zu sein, müssen wir das Gleiche tun. Bayern soll zu einem Quantum Valley werden und in Ergänzung mit KI dann zur führenden Region in Deutschland für diese Bereiche. Und die französischen Partner sind ähnlich stark. Wenn ich mir das in Paris anschaue, was hier alles investiert und vorangebracht wird, ist das genau die Brücke. Ich selbst habe mit Präsident Macron genau über diese Themen geredet und wir waren uns einig, dass die eine Motorfunktion gerade in der deutsch-französischen Freundschaft ausgehen muss und Bayern ist da ein bisschen das KI-Herz von Deutschland. Und was zur Kultur noch zu sagen ist: Wir tun das in anderer Form, als früher geforscht wurde. Früher war Forschung nationalistisch. Sie sollte im nationalistischen Wettbewerb für die eigene Klientel Vorteile bringen. Das ist anders. Diese Ideen, die wir haben, ist auch eine Einladung an die Welt, an junge, schlaue Köpfe, an junge Brains, an junge Frauen und Männer, die sich mit Forschung international weiterentwickeln wollen. Forschung von heute ist keine vertikale Einrichtung, die sozusagen vom Staat verordnet wird, sondern sie ist international. Sie ist horizontale Netzwerkstruktur, die dahinter steht und sie soll auch ein Moment der Freiheit sein. Forschung und Freiheit gehören eng zusammen. Und deswegen ist das, was wir heute leisten, nicht nur ein Beitrag, der am Ende wirtschaftliche Möglichkeiten schafft, der das Leben verbessern kann durch Umwelt, Klima und auch Gesundheitsmöglichkeiten, sondern es ist auch ein Beitrag für Freiheit und Demokratie. Insofern tolle Geschichte, viel Erfolg.
Welcome back to the symposium. It is now my pleasure to hand over to our first speaker, Francis Bach from Paris, and he will speak about the convergence of gradient descent for neural networks.
So, thanks, Daniel. So can you let me put my video?
We see the slides.
Sure, but my video, it said that I cannot start the video, which is fine. But
no, just a second. Sorry about that. It's showing my video. That doesn't make sense. Right. Can we somehow include the video of Francis?
I've put a nice shirt.
Does it work now?
Let me check. Yes, it does.
Great.
Should I start, Daniel?
Go ahead, Francis.
Oh, thanks, Daniel, for the opportunity of talking at this nice workshop. I wish I was in Munich, but hopefully next year we'll have some nice time there. So today I'm going to talk about joint work with Henry Schitzer, who's a researcher in the south of Paris at Orsay. And the scientific context, I guess you're all familiar with. So there's more and more data everywhere. And what I want to emphasize just here is that it goes beyond marketing and social media. A lot of scientific domains have lots of data, and this goes from usual suspects like bioinformatics to more recent fields like humanities. So all of these, they want to treat their data in a sense automatically. And in recent years, as Daniel has said, there's been more and more use of learning algorithms in various forms, and the so-called intelligence is obtained from a combination of models, algorithms, data, and some computing power. And today I'm going to look at the algorithmic part and trying to understand why it works. Okay, so trying to provide like mathematical guarantees on the predictive performance of learning algorithms. So why would you want to do that? First, because it's satisfying on its own, but also because it can provide guidance to practitioners, and I will come back to that in a moment. So let's jump into it. So I'm going to consider the classical parametric supervised learning, which is the main application of machine learning in AI. I have some data, xi, yi. Xi can be an image. Yi could be a label on that image. I observe n of those, like many pairs of observation xi, yi. The goal is, give me a new x, a new image. How can I predict the label on that image? This is typically done by some prediction function, which is parameterized by some vector theta. And the classical prediction functions that people have been using for the last 50 years or more. The first is linear predictions. So you just take your data, build some feature vector, and linearly combine the various elements of that feature vector. So this is used a lot, in particular in advertising, in many areas, in industry and science. So here the difficulty is that both n, the number of observations, and the number of features is typically very large. But then for problems such as computer vision or natural language processing, we need more flexible models that combine linearities, okay, with the non-linearity. And here I put the example of a neural network where you start from your input x, let's say an image, and you multiply by some linear function, and like before, but now you take some non-linearity, and by combining these linear functions and non-linear functions, you get a deep neural network, which is now the state of the art in many areas. So here again, the difficulties are also both n, the number of observations, and d, the number of parameters is quite large. So how is it? How do we learn from data? So most frameworks will end up minimizing some form of the risk on the data. So you count the number of mistakes you make on the data, and you want to make that number of mistakes as small as possible. And this is formalized by minimizing some loss. So you average over your training data some loss between what you want to predict, yi, and your predictions, which is there. And you add some regularizer to avoid overfitting. So you want to predict well on unseen data. So here, this is just a mean to an end. The goal is not to do well on the data that you see, but on unseen data. I will not come back to it, but I want to emphasize that really what counts is error on testing data. All right, so let's look at the math behind it. So I've mentioned two types of predictors. And so for the first type of predictors, like linear predictions, then the theory and the practice is pretty well understood. Okay, the reason being that if you have a convex loss, which is typically the case, then you get a convex optimization problem. And in the last 30 years and more in the last 10 years, there have been a sequence of very efficient algorithms with quantitative runtime and a prediction performance guarantee. So even before you start the algorithm, we can tell how long it's going to take and essentially how well it can predict on top of the optimal predictions. So this has led to what I call the golden years of convexity in machine learning. And the dates are arbitrary, but this led to supervector machines like in the late 90s and early 2000s, a lot of sparsity inducing norms, and many other areas where convexity was used a lot. Okay, so this corresponds to linear models. Okay, and this is what is nice is that in the exchange between theory and practice, so you can both practice can benefit from theory because it can provide like some improvements, like acceleration, for example. Question is, what about deep learning? Okay, so let's look at the simplest form of deep learning. So this is clearly a simplification. Nobody is using this for computer vision. This is more complex. You need like convolution layers plus pooling and so on. But let's look at this one. So there are two main difficulties. The first one is that the problem is non-convex because I have some nonlinearities, and this will be the main topic of this short talk. Another difficulty is the fact that in practice, people tend to use what we call over-parameterized networks, where the number of parameters can be far above the number of observations. Okay, so in the statistical sense, this may cause problems, and there are a lot of work trying to do that, and that shows reference at the end of the talk. But I'm simply going to use this like over-parameterization for a computational advantage, and this will be the goal of the talk. How can we leverage over-parameterization to deal with non-convexity in those like neural network problems? All right, so what can go wrong with non-convex optimization? A lot of things, and the key issue is that you may have some local minimum. Okay, so this is a 2D profile where you have one global optimum over there, like a few local minima, some saddle points, and when all like gradient-based techniques will not be able to differentiate between getting stuck there or getting stuck there. Okay, so this is the usual problem of trying to go beyond local guarantees. So in general, unless you make extra assumptions, you will not be able to escape those local minima. But the goal will be to study a particular form of non-convex optimization problem and try to see if you can get some guarantees. So I'm going to consider an even simpler network, just the first network, which is a nonlinear function of its parameters. Okay, so I have one, I start from X over there. This is my data, could be like pixels. I multiply by θ1, a matrix of weights, which I will put the input weights. I get the so-called hidden layer after taking some nonlinearity, sigma. So sigma typically is taken component-wise, and sigma can be the sigmoid of the positive part, the ReLU. And then once I've computed those hidden neurons, I can compute the output neuron by just linearly combining those output weights. So as you can see, there are two sets of weights, the input weights and the output weights. Okay, so this is a nonlinear function of X. And on top of this, I will try to minimize the risk. Empirical risk or expected risk doesn't really matter. But what matters is the fact that the risk is convex, because the loss is convex. So if you use a cross-entropy loss, this is a convex function. So even in the deepest network, the loss is typically convex. So why are we focusing only on this single hidden layer network? Is because we need for our result that the prediction function is a sum of terms. Each of those terms need to have its own parameters, and there should not be any sharing of parameters. So here, H, you get a sum over all hidden neurons of all the input weights associated with that neuron. Okay, take a nonlinearity over there, and then combine all of those separately. Okay, so we have a parameterization in terms of WJ, which for neuron J, WJ will be the concatenation of the input weights here and the output weight over there. And this is what we need. So this will not extend directly to deeper networks. So what is the main insight behind this work? I will not go into the details, of course, is that we're going, as you get over-parameterized, you get a sum with more and more terms. Okay, so, and you can see this sum, or this average here, as the integral over the feature of a function C of W times some measure. Okay, so you get equality if the measure is a weighted sum of Diracs. And the key insight behind those like so-called mean field approximations is that as you get more and more neurons, okay, over-parameterized, you end up minimizing over a measure, okay, with a given density mu of W. And the whole area of mean field techniques for those like neural networks is to analyze what's happening when you deal with those densities. This is not a new idea. Okay, this dates back from Brown from '93 and even earlier probably. And here this is just like instantiated on neural networks. So how are we going to learn those like parameters? By gradient descent, which is called backpropagation in that setup. So you minimize the risk over your sum of hidden neurons. So we're going to consider not gradient descent because it's a bit too complicated, but the gradient flow, which is the limit when the step size goes to 0, and which provides some ideal version of gradient descent of the stochastic version. We're going to analyze what's happening there and trying to provide some qualitative results. So first result is what's happening when m goes to infinity. So when the number of neurons go to infinity, can I define and understand what it means? It has a name, so it converges to a so-called Wasserstein gradient flow. So if I had more time, I would like make the link with the optimal transport. But here, I just need that this object to have a name and to be well defined mathematically. And the goal will be to understand. If this object, so if the flow, so you have like a moving set of measures, does it converge to the global optimum? Okay, so here we know as a fact that when you minimize over neural networks, you may get stuck in local minima. Because there is like years and years of experiments showing this. Here, what can we make? What can we do so that we are not getting stuck in this in any local minima? So this is joint work with Henry Schitzer, and we have some informal theorem. If you want to know more, you can look at the statements and the precise definition in the paper. And we need two key ingredients. This is not true in general. If you minimize functions by gradient flow, you don't get the global optimum. We will need first homogeneity and a good initialization. And in terms of homogeneity, we need some full of partial homogeneity, meaning that if you multiply your parameters by a constant, the output is multiplied by that constant or power of that constant. This is true for neural nets with respect to the last layer. And if you use like rectified linear units, this is true even globally. We also need some like sufficiently spread initial measure, which is a de facto practice. People sample like neurons at random, and this is what we need as well. So let's see. So first, big caveat, this is only qualitative. Okay, I will come back to that in a moment. But before that, let's show how this works on a very simple like setup. So when I'm predicting from two-dimensional inputs, okay, so this is the neural network, and I'm assuming that the data are generated with a neural network with 5 neurons, and I'm representing here the direction of those 5 neurons. So as I learn, I will generate many neurons, update them by gradient flow on the risk, and the goal is that those 5 neurons end up, or the neuron that we learn end up along the direction of those 5 neurons. So if I get along the correct directions, I've learned the correct function. If I don't get the correct directions, I have not learned the correct functions. So here, I'm trying with several numbers of neurons for learning. All those numbers, 5, 10, 100, are enough to learn the function perfectly. So if I don't learn the function perfectly, this is because I have a local minimum problem. Okay? And what our research suggests is that with many neurons, then all neurons should end up in the correct directions, which is what we observe in this small experiment. On the left, with only 5 neurons, you have enough to learn perfectly, but to get stuck in local minima. The intriguing aspect and the open problem is what's happening in between. Okay, so you want to take like millions of neurons, you want to take like a small number, and it turns out that if the number is reasonably larger than 5, the minimal number, then it still works and it's still like not understood. Let me give some small video just to show that the dynamics is quite complex, because the neurons, they start from, so let me start again. No, don't want to start anymore. That's fine. So the neurons, they start from the middle and then they end up like moving into the correct directions. All right, so to conclude, I've tried to provide some qualitative analysis of gradient descent for 2-layer neural networks. So here the take-home message is, if you take the exact number of neurons that you need to optimize, then it won't work. Okay, it may not work, and in practice doesn't work. Okay? We don't show that if you have too few, it doesn't work, just like practice. And what people have done in the last like 10 years is to take more and more neurons. And our result provides some qualitative reason why. And I say only qualitative because at the moment, we are not able to say that how many neurons you need to achieve this mean field limit and how much time it will take. Another aspect which I didn't cover is what does it converge to? Okay, can I show that even in this over parameterized regime, which could be a problem for generalization, we can still generalize. And there is like follow-up work also by Lenaik and me, showing that it does converge to a maximum margin separators, like SVMs come back, strike back. And if you want to know more, you can look at this page. In terms of open problems, then there is like a lot of open problems at the interaction between theory and practice. Clearly being quantitative, because this is really what we want, to be able to say a priori how big the number of neurons need to be and how much time it will take. Of course, extensions to convolutions and deeper networks, this is quite difficult. And I want to highlight as my final sentence the importance between the relationships between theory and practice. I think, of course, you need algorithms that work well in practice, but if you want to go beyond like simple applications, in particular to safety critical applications, understanding the behavior is important, and hopefully we'll see examples in these workshops. Thank you for your attention.
Thank you, Francis, for this wonderful talk, and also thank you for setting a premier example of being exactly on time. Very good. We have time for a few questions. Is anyone interested in asking a question to Francis? If you have a question, you can just post Q in the chat and then I can call you. Or possibly you can just speak up as well. Maybe I'll have a question myself then. This is a very interesting endeavor that you're making, trying to prove global convergence. Can you say how difficult do you expect it to be to go beyond 2 layers? Let's say if you were to tackle 3 layers or 4 layers, well, how would the computational complexity of this approach increase?
I expect it to be quite difficult, or at least based on 2 years trying to do it. So the problem is that as soon as you go beyond like 2 layers, then you get a lot of parameter sharing. You can define some mean field limit, and you get a set of partial differential equations. You can write them, but analyzing them starts to be very difficult, and nobody has been able, we're not the only ones working on this. Nobody has been able to get any reasonable answer. One possibility is to look at different types of networks. Okay, so maybe go from fully connected to like ResNet. So ResNet is a bit easier to understand because there's a well-known link with differential equations as the depth goes to infinity. But for like multi-layer, fully connected networks, things are quite difficult. And the other difficulty is that 1 layer is already enough to be universal, okay, to learn any function, like to approximate any functions. So the need to go, with that analysis, the need to go from 2 to 3 layers is not clear from the theoretical standpoint, and it is still open how you can characterize the benefits and performance of 3 layers. Clearly, people see it in practice, but we're still like not able to fully characterize it in theory.
There is a question from Jean-Bernard. I don't know, Jean-Bernard,
yes.
Can you?
Yes. Did you try to see the effect of regularizer in the experiments?
Oh, yes. Thanks, Jean-Bernard. Indeed, it's quite important. In fact, Henry Schitzer has a follow-up paper where he puts on the classical L1 penalty. Okay, with an L1 penalty, which happens to be very easy to put in this framework. Then you create some sparse measure. Okay, so if you, let's go back there. So here, if you put extra penalty, then you converge to like a singular measure, okay, almost surely, and you can characterize precisely how you can converge in the speed of local convergence. Okay, and so there's a nice paper by Lenaik last year at MatProg doing this. So clearly, you can regularize to make the analysis easier, but the fact that it does converge to global minima does not require regularization, because here, in those experiments, we use like infinite amount of data by having like a stream of data and doing SGD. So we don't need regularization to overfit, to avoid overfitting. It helps in terms of optimization.
I actually had a question as well. Francis, do you actually see this as an explanation for that distillation works well? So often people like train large networks and then distill it to smaller networks, and this seems to be an explanation for that, right?
I'm not familiar enough with distillation to say anything like interesting. The problem is that here I don't believe this is an explanation, because here we need, even if you learn on the output of your previous network, our result still needs to have lots of neurons. Okay, so this does not explain why you may need fewer neurons. It just explains that what people have been doing through as much compute as you can of the problem is working in a sense, okay? And which is like sad in a sense, because just throwing compute at the problem as a solution is not what I prefer, but this is what this thread is suggesting. Throwing like lots of neurons will help. Of course, we're trying to see if we can reduce that number of neurons, and distillation is one way of doing it. And clearly, this is an interesting question, but we have no clue on how to do it.
Right, but basically you're saying if you have 5 neurons, you would still find a solution, right? There is a global minimum. So
with 5 neurons, take on the left, we don't find we know the solution has 5 neurons, and if you start with 5, we don't get it. But there is one, right? There is one. There is a solution. It's not there's no solution. It's not global. It's what you could expect is that if at the end your neural networks has only like a small number of active neurons. Okay, so if you take these hugely over parameterized networks, because of the RLU, many RLUs are in fact equal to 0. Okay, so you could expect that only a few are active, and then what we suggest is that if only a few are active, if you take a few times or 10 times this number of a few, then this may work.
Okay. Thank you, Francis. Thank you, everyone, for the lively discussion. In the interest of time, I would like to hand over to the next speaker, who is Philipp Hennig from Tübingen, and who will speak about probabilistic uncertainty in computation.
Thank you very much. Let me see if I can rearrange my screen as well so that I can talk. Okay, so I hope you can see my screen. Thank you very much, Daniel and the organizers, for putting together this great event. And thanks to Francis for taking this fun right before me. It's always great to give a talk right after Francis. First of all, I get to inherit your YouTube audience. I also get to show off my shirt. I actually put one on as well. And secondly, this is like the perfect introduction for me to talk about, to take you maybe all out there in the YouTube as well on a deep dive into the computations of machine learning. Francis just told you why they work, and now I'd like to convince you how I think they should work, how they should work. So when we talk about machine learning, people often describe machine learning as a computer algorithm that fits or adapts a model to some data so that it can predict the data better. And that's a good description, but as you just heard from Francis, it's not a good explanation of what actually happens inside of the machine when it learns. Because what happens there actually is the solution of a numerical problem. So the solution of a mathematical problem that has no closed form solution. And this is in contrast to classic AI, which is tends to use problems that computers can actually solve. So these problems are integration problems for probabilistic machine learning, and as you just heard from Francis, they are optimization problems for statistical machine learning. They are the solution of differential equations, maybe to simulate the evolution of optimizers when training deep nets, or to predict in general anything into the future, also for reinforcement learning and lots of applications of machine learning. And they are linear algebra as the base case of everything I just described. So numerical problems are not new. They are much older than machine learning. And that means that there are algorithms out there that were already invented for all sorts of other applications over the course of the past, well, let's say, century. And that's great because it simplifies our lives a lot. We can just use those methods as they lie around and are available to us, and most of us actually do this. But this has downsides. It can be dangerous. At the very least, it can be inefficient. because machine learning patently poses some problems for which the classic numerical algorithms are ill-equipped to address them. One such problem that Francis just brought up in between the lines is the drastic reduction of numerical precision, the stochasticity of the computations involved in machine learning that are caused by, for example, data mini-batching. So I would say that we need new numerical algorithms for machine learning that address the pertinent challenges of our field, and how convenient then that the numerical methods actually are learning machines themselves. A numerical algorithm estimates an unknown quantity, like the value of an integral, given the result of tractable computations, like the value of the integrand at various points. Or it estimates the location of a minimum, given the values of gradients on various mini-batches. So numerical algorithms estimate a latent quantity from data. They are learning machines. They are active learning machines because they even decide which data to collect. And the only difference between a numerical algorithm and a learning machine is that the numerical algorithm uses the CPU or the GPU as its data source, while learning machines tend to use the hard drive as the store for data. And it's therefore possible to phrase numerical computation itself in the language of machine learning, in particular in the language of probabilistic machine learning. So, as an application of Bayes' theorem, the computation of an unknown quantity z, let's say the value of an integral, given the result of a bunch of computations and some modeling assumptions by multiplying a prior with a likelihood and dividing by the evidence as Bayesian inference. This viewpoint on computation is called probabilistic numerics, and it turns out that many of the traditional numerical algorithms, actually pretty much all traditional numerical algorithms, can be phrased in this view as well, and they just turn out to be maximum a posteriori estimators under this assumption, under some pretty generic priors typically, and pretty specific likelihood functions typically. Now we can use this view on the traditional methods as a great starting point to create something new, right? You can use the existing methods as an example of something that works well, and now apply the levers, the power of probabilistic modeling that machine learning has been working on for several decades now, to improve these methods a little bit, to adapt them to the needs of contemporary machine learning. For example, we can use specific priors that capture salient aspects of specific types of problems to reduce their complexity. We can use, and this is a very powerful idea, the likelihood as an explicit way of encoding imprecision in computations, such as, for example, for mini-batching, and then track the effect of this uncertainty through the computation. And you can use the evidence as a generic way to adapt hyperparameters of numerical algorithms in machine learning, which I hope many of you will agree with me is an important task, because at the moment practitioners spend a lot of time and energy and resources on tuning these hyperparameters. And we can use the posterior to, as a universal way of capturing uncertainty about the result of a computation and hand it forward to whatever comes next, propagate it through the chain of computation. So to give you an example of how this could work, I'm going to show you one example with differential equations, because I'd like to convince you that taking this viewpoint doesn't just mean changing the way you think about a computation, but it actually can mean a tangible change in the way we use numerical methods. And in particular, I'd like to convince you that this allows us to, or maybe it should tell us, to break up the notion of a black box numerical algorithm that just comes from a library and take ownership of the algorithm ourselves. So for that, let me talk about differential equations once again. So thankfully, Francis already had one in his talk, so I can maybe be pretty quick here. A differential equation is an implicit statement about an unknown curve. In this case, it's an ordinary differential equation, an implicit statement about an unknown curve x of t, which is only defined or identified by two pieces of information. One is that the derivative of this curve through time should be equal to some nonlinear function that depends on the value of the curve everywhere. So the unknown solution to the ODE should follow this vector field that's shown here in black in the background. And we know that the curve goes through some initial value, some point at the beginning, this little dot here. These two pieces of information together actually uniquely identify a curve. In this case, it's this very simple black curve here. But in general, of course, we don't know that. So we need a numerical algorithm that does that for us. So let me show you how a probabilistic ODE solver would do that. And spoiler alert, it actually does it in pretty much exactly the same way that a traditional ODE solver does that. We know that the curve has to go through this point. That means we can evaluate the vector field at this point, and that gives us two pieces of information, a function value and a gradient that we can condition some regression algorithm on. In this case, it's a Gauss-Markov regression algorithm, a fancy word for a Kalman filter. And that algorithm then allows us to predict into the future what the solution of the ODE might be, probabilistically speaking. And if we can use this to build a new point where we can predict what the true solution is, not an infinitesimal distance into the future, because then solution would take forever, and not a very large step into the future, because then the prediction is very bad. So we have to find some intermediate sort of point that has something to do with the regularity of this vector field. If we can find this step size, then we can use this prediction to construct, to collect a new observation of the gradient, the pseudo gradient of this curve, by evaluating the vector field again. If we do that, we can then condition on this observation and continue iteratively in this fashion, and we get an estimate for what the solution of the ODE is. Now, as I've already told you, these algorithms actually are pretty much in structure, even though I phrased them as a machine learning problem, essentially, very, very closely related to how classic multi-step solvers work. And in fact, they inherit some of the great properties of these methods. In particular, if we increase the computational resources, so if we reduce the step size of the algorithm, then this red line, the point estimate, converges to the black line at a high polynomial rate. We can make that rate up to 8 or 11 or whatever the good classic ODE solvers have as well. And the region of uncertainty around this estimate, so this yellow region here, contracts at a rate that can be shown to be a worst case estimate for the actual distance between the black and the red curve, between the true solution and the estimated solution. And so it's possible to build these algorithms in a way that they inherit essentially the same computational complexity and the same theoretical guarantees, and on top of those provide some error-bound guarantees, such that the code itself also becomes essentially a drop-in replacement. So there's now a library called ProbNum that you can easily install in your Python environment that can act essentially as a drop-in replacement for the kind of ODE solvers that you're used to. Now, if I tell you that, then you might be saying, okay, that's all nice, it's like a little finger exercise, but what should I actually do with such a solver? Because I already have this one. Why should I have something as a drop-in replacement if all I get is a little bit of extra samples around the solution? Normally, I try to solve my ODEs with high precision anyway, and then why should I need to do this kind of, use this extra kind of functionality? Well, the reason for that, in my opinion, very rare in contemporary data science and machine learning to encounter such a reduced textbook example of having to solve an ODE. In practice, things are, of course, much, much more messy, and the way that the ODE solver interacts in the problem is actually a little bit cumbersome. So let me show you one concrete example of where an ODE might show up in a prediction problem. And if I just show you this data set, I don't have to explain to anyone what this data is, because most of us have spent way more time than is healthy looking at data like this over the past year. So these are the COVID numbers of Germany for the duration of the pandemic, the raw numbers actually. So if you find yourself looking at this kind of data as a totally naive data scientist, not a modeler, in like early 2020, in April 2020, then you might have thought for yourself what you would need to do to use this data to predict into the future, to predict the future dynamics of this pandemic. We actually do this in undergraduate courses as well with our students. Now, a naive first idea you could have as a sort of a strawman machine learner is to use an unstructured, purely data-driven regression algorithm, like, you know, a deep net or a kernel-rich regressor or a Gaussian process regressor. So you'll quickly find out that that doesn't work well because it doesn't capture the structure of this problem at all, right? It's going to predict and extrapolate in a very boring kind of way depending on which model you use. And this is because this purely data-driven view on machine learning doesn't capture mechanistic knowledge. It doesn't capture the causal knowledge we have about how this data actually comes about. And the other extreme alternative is to use a purely mechanistic model, one of these differential equations like this SIR and something else model. So here I've also included the V for vaccinated. You'll see that in a moment again. Such models are, you might call sort of traditional mechanistic models. So they're phrasing the future dynamics of the pandemic in terms of an ODE, some complicated ODE here. And if you've ever used SRR models yourself, then you know that they by themselves are also not great ways of modeling pandemics, because SIR models essentially assume in their raw form that initially you get an exponential growth until herd immunity is reached, and then you get some flattening out and some kind of logistic curve. Now, we all know that that didn't happen. Nothing like that happened anywhere in the world. Instead, governments stepped in, like, for example, the government of Markus Söder, and they introduced lockdowns and social distancing measures and all sorts of policy decisions to reduce the case numbers. What that amounts to is that there is somewhere in this ODE a bunch of unknown factors, some latent forces that I've here summarized in this very simple way into some kind of contact rate, beta. Now, unfortunately, we don't know that contact rate because it doesn't get measured. The only thing we know is this course of the case numbers. And what you'd of course like to know, and this is a question of important political implication as well, is what is the contact rate? What is the effect of these political decisions on contact rates? So we need a model to infer those quantities. Now, unfortunately, our software landscape doesn't provide really the right tools to do that. What we have is a little bit clunky, and we have to sort of glue it together in a way that it really wasn't ever meant to be. On the one hand, we have ODE solvers, which are black box methods that require us to tell them what the correct ODE is, and then they'll give us a point estimate of the true solution. We have regression algorithms, which allow us to use data to fit some latent model, but it's hard to tell that model that there is an ODE underneath driving the dynamics. And if you're an applied mathematician, you might know that this problem I just described is also sometimes called an inverse problem. So it's a setting in which there is an unknown ODE, the solution of which we get to observe with noise, and now we'd like to know what the unknown ODE is. Well, unfortunately, these inverse problems are really just a fancy wrapper around this black box. So if you go and try and solve an inverse problem, then essentially you just have to solve ODEs over and over and over again forward through time. That's a highly inefficient way of using computational resources, and it's really just caused by the fact that this is a black box, that we don't get to fiddle around with how ODE solvers actually work. They are just there. They are in SciPy, and they just have to work. What we would like to have is a probabilistic program, something that relates all of the unknown quantities to each other. There's some unknown latent force, some contact rate that defines the ODE. Then we use an ODE solver to predict what the solution actually is. That solver has some own numerical error that we might want to control and guide, and then we observe the dynamics of the system. Now, if I tell you that an ODE solver is really just a Kalman filter, and even the traditional ones are essentially just Kalman filters that keep track of some latent state of quantities that evolve over time and just conditions those states on what you might call an information operator, so ideas, observations of the vector field, and the fact that those observations of the vector field relate to the derivative of the curve, then it becomes quite natural to say, well, that very same algorithm could also condition on observations of the data. And then those two sources of information, the mechanistic and the data information, can be combined in one joint algorithm directly. And if there are some parts of the state space that affect the ODE that we don't get to observe directly, well, that's not difficult. It's just part of our latent state. It's just part of the Markov chain that we have to model for our Kalman filter. We did that recently in a joint work with Jonathan Schmidt and Nico Kremer. It's currently now in the archive. And so here I'm going to show you a little bit what this algorithm does. What you'll see here is up at the top in this yellowish bit, that's not the incidence rates, but it's the number of infectious people in Germany over time. In the middle, you'll see the contact rate, so the bit that we don't get to see, that the algorithm has to guess and observe. And down here, I'll plot the number of susceptible people in green and the number of vaccinated people in red. I could also have plotted the number of recovered people, but it's actually a relatively small number, so it's difficult to see in this plot. So the data is already there, but the algorithm hasn't seen that data yet. It's just going to observe it over time as we predict, as we move forward through this time series. So the main thing to keep in mind here is that what we're going to see is not a repeated solution of an ODE, but a single pass through the data. And also I should say, of course, none of what I'm going to show you is actual COVID research, right? It's just a master's student and a PhD student and me trying to sit down and build an ODE solver. So please don't use the numbers you're going to get to see to decide when you can go on holiday or not. So what the algorithm initially does is it just predicts the dynamics of an SIR model. It doesn't predict the simple extrapolatory behavior that you would get to see from a regression algorithm, but it predicts this kind of extreme exponential increase because it hasn't seen any other data that would tell us that that's not true. Until we see, in Germany at least for our first wave, the breaking of the first wave and the numbers started to decrease, and then the algorithm has the only way to explain why that happened is that the contact rate in Germany had to have come down during that time. Now, over the summer of 2020, the case numbers in Germany were relatively low, and as an effect of that, the algorithm becomes quite uncertain about the contact rate, because if you have few people around who can infect other people, you have few people that can act as probes, essentially, to measure what the contact rate is. So the algorithm becomes uncertain about the contact rate until we hit the second wave, and then the algorithm becomes confident again about what the contact rate was, and also uses the contact rate to explain the dynamics, the changes in up and downs in the second wave that took so much of our mental capacity during that time. And then towards the end, the algorithm starts predicting actually a kind of a third wave until the vaccination rates actually go up. And about 2 weeks or so ago, the algorithm finally started predicting that we'll see a drop in case numbers. So at the end of such a single pass through the ODE, you can then do a smoother pass backward that doesn't cost anything and produce samples. And you have non-parametric prediction of a latent force that involves an ODE by solving a single ODE forward once through time, rather than a repeated solve over and over and over again. So that's a change in the way we look at software as a collection of algorithms within machine learning. So I'm at the end. I hope I've stayed roughly in time. What I'd like to convince you of was that computation is an instance of inference, and therefore it makes sense to break up the separation between numerical algorithms and learning machines as separate entities and treat them as one joint thing. If you'd like to know more, then please check out our website where we have these papers as well, and you can try and play around with this kind of pieces of code yourself with our open source problem library. Thank you very much.
Thank you, Philipp, for this nice presentation, for this wonderful overview. Do we have questions? Maybe one question from my side directly to get things started. You mentioned how you can combine measurements and observations with ODEs and to model the underlying problem. A lot of problems cannot be really modeled with ODEs, but you would have to revert to partial differential equations, for example. I don't know, lots of phenomena in maybe fluid mechanics or whatever. Can this easily be generalized to PDE-based approaches as well?
I would say it can be generalized. I'm not sure I would use the word easily. You might have to wait for a few more preprints from us. No, so of course, this is of course the kind of natural next question to ask, and it's definitely something that we're working on. PDEs are also, let's say, numerically a little bit more challenging, largely because the state spaces are much, much larger. There's a bit more structure to take care of. And PDEs as a field are much more evolved than ODEs. So if you want to build something that is reasonably competitive with what a PDE person would propose, you have to spend a little bit more time thinking about how to do that right. So we're trying to do our homework there, and that requires us to take a little bit more time. But conceptually, there is not really a reason not to apply this kind of approach to PDEs as well.
We also have a question from YouTube. Someone is saying, thanks for the very nice talk, Philipp. ODEs are the future. If your data is sparse, if you only have sparse observations, how do you train an ODE?
So actually, I would face it the other way around and say the ODEs are a wonderful way of replacing data with mechanistic knowledge. So, and I mean, SRRD models are an example of this. When you have no data, you can still predict into the future much better than you could without mechanistic knowledge, because you can at least you know what kind of forces are going to drive the dynamics of, well, in this case, the pandemic, right? Now, of course, if there are latent quantities in your data, like this latent force here that you just don't know, then you'll just be very uncertain about the prediction, as we are here on the right-hand side still. Mm-hmm. But I think that's a good property of such a model.
Someone's asking, saying, great to see numerical solvers on the corona case numbers, but how do you access the truthfulness of the results from the probabilistic solvers in general?
Yeah, so, okay, so there's two kinds of answers, right? The one that's a mathematical answer, the one that I kind of hinted at with this little picture, that we know that these ODE solvers themselves, as such, inherit many of the great properties. I'm citing a bunch of papers up here sort of really quickly. There has been extensive theoretical work on showing that these filter-based ODE solvers have good numerical, mathematical, analytical properties. They have high convergence rates. They have good global error. They have the error estimate is meaningfully captured and calibrated. There's also practical work on showing that they actually practically calibrated. Now, of course, there is a political question underneath this kind of model, right? Well, this one, right? So should we trust those numbers or not? And so for this, that's why I had this caveat here, right? Please do not trust them, because of course a good model for COVID dynamics is much, much more complicated than the kind of thing that two students of mine and I would write down in an afternoon. It's much, much more complicated than this simple kind of ODE. And that's why there are good research groups out there in France and in Germany and elsewhere in the world building really good predictive models for COVID data. So I wouldn't trust this model at all. It's really just a case, it's really just a proof of concept that this kind of functionality can be created within machine learning pipelines.
So you're saying I should stop my vacation booking that I just did based on you?
Yeah, maybe, yeah. Try and listen to actual modeling experts that have much more high-dimensional and structured geographical models.
Okay, thank you, Philipp. Thanks everyone for the lively discussion. We'll take a 15-minute break and reconvene at 10:10 with, I think, Bernd Bischl from Munich.
everyone from the coffee break. We are gonna start the session with Bernd Bischl from Ludwig Maximilian University in Munich, and he's gonna talk about auto machine learning.
Okay, yeah, thank you for the kind introduction. Welcome to my talk. Yes, I will give a pretty high-level talk regarding AutoML. I will mainly want to actually address here a couple of current challenges and research directions and underexplored issues that we might want to focus a bit more on during the upcoming years. And I will also, of course, outline a couple of papers that we have already written to address these issues. And as often in these cases, I'm not presenting completely only my own work. So I have a pretty large research group of, including Yannick here as a postdoc and many PhDs whose work I'm also representing here pretty proudly. So let me give you a super rough and quick introduction to AutoML. You all probably know this, so I will keep this reasonably short. So how does a usual machine learning workflow look like? Yeah? So usually we have to select some appropriate model class that we want to apply to our task. An ML expert usually is now running pre-processing and feature extraction to make the data compatible with the model. Usually we also know that this is where most of the hard work actually goes in nowadays. And then we try out different hyperparameter settings, pre-processing options, configurations, and so on. And if we iterate the above, which is usually necessary, this is a very time-consuming process, and many parts, especially this configuration of algorithms, should be mapped to a computational optimization process rather than trying this out manually. Usually this is nowadays addressed through a generic black box optimization loop. So we have become pretty good at that during, as a community during the last, let's say, 15 years. And we're in this generic black box optimization loop, a new hyperparameter configuration, or sometimes also in a batch proposal, like manner multiple configurations are proposed. They're evaluated by resampling, cross-validation, and so on, usually with respect to a single performance metric. Then the optimizer is somehow updated, and we iterate and hopefully converge to at least a well-performing optimization. Usually reaching the global optimum is pretty unrealistic in the practical scenarios we have to deal with in HPOs nowadays. But at least we would like to converge to something that works well for the task at hand. We can also map the model and operator class selection problem. So that means which model should we use with pre-processing or feature extraction option should we use to that process, to that black box optimization process, by either designing that through categorical choices or representing that as branches in computational graphs. So here you can see a pretty simplified scenario where we optimize over also the pre-processing choice or over the machine learning model at the end of the pipeline. And this usually gives rise to categorical parameters and a hierarchical parameter space with subordinate parameters. So that usually makes the setup of, that usually makes the structure of the parameter space considerably difficult. So we are now dealing with something that's black box, that's expensive, that's stochastic, but that's also in terms of the parameter space that's mixed, integer, categorical, numerical, and hierarchical. So pretty ugly as an optimization problem. And these are the usual suspects that we nowadays use to address this type of black box optimization problem. So there are evolutionary algorithms. They are a little bit less used for classic HPO. They are much more in favor nowadays for neural architecture search types of problems. There's Bayesian optimization, and then there are multi-fidelity approaches. For example, in its most simple form, there's hyperband that tries to address the multi-fidelity problem or exploits the multi-fidelity aspect of machine learning in the sense that we can evaluate most algorithms through a so-called budget parameter, and through that speed up the optimization considerably by killing off badly performing configurations early on. And of course, as usual in these cases, we are nowadays mixing these approaches. So there's, for example, BOP, so Bayesian optimization combined with hyperband and so on, to combine the best of these two worlds. Now, I guess most of you have seen this here. I'm pretty sure everyone has seen Bayesian optimization and knows how this works. Yeah, that we are mapping the configuration space to an outcome variable, that we are doing that usually through nonlinear, non-parametric regression. So usually through a Gaussian process, or nowadays also through random forests or deep neural networks. The important thing about this is that we usually need, in addition to the posterior mean function that we are mapping, that we're modeling here in a nonlinear fashion, we also need something like a local uncertainty estimate, so a posterior variance, in order to combine the two into an acquisition function which balances out exploration and exploitation. A usual candidate for this is the expected improvement. There are many variants nowadays to model this trade-off differently in BO. Now, what are some current challenges for AutoML? What doesn't work so well currently in this scenario? So it is still pretty unclear what the best HPO approach currently is. So the benchmarks are still somewhat lacking in my opinion. This is, as always, very hard work. So it's also very often not that popular work, I would say, in the community. But I guess as it's very hard to prove things about this which are practically relevant, I think as a community we should invest much more here. It is still at least not perfectly clear how we should integrate human a priori knowledge. It is also not ideally and perfectly clear how we can transfer experience into AutoML. Of course, there are many different approaches nowadays that allow us to do something with warm starts, to somehow learn search spaces and so on. And I think these issues here are pretty important because AutoML, or let's say HPO, is either too hard to configure for users as an optimization process, or we are kind of using arbitrary decisions here, at least to some extent. What I usually also see much less addressed is a multi-objective formulation of HPO. So in many practical scenarios, I would say that there is not one performance metric at work, but that we should rather optimize a trade-off between different metrics. Often interpretability and sparseness should be included there. And AutoML as a process itself is also too much of a black box that hurts adoption a lot. So there are quite a few current papers that discuss exactly that through user interviews, and that show that many people are reluctant to use AutoML to its full potential because they just don't understand what happens inside of the process. So let me now at least give you a short glimpse of a few things we have done in this area here. So I'm also checking my clock a little bit, so I'm not running totally over time. So we have, since the last 12 months, I would say, created a pretty extensive systematic AutoML benchmark. This is completely open source. This builds upon the OpenML platform that I'm also a part of since many years. It's a pretty fair and easy to use comparison. You can just plug in your own AutoML procedure in there if you're developing that and get that automatically benchmarked and compared to many standard tools that are already integrated. So at the moment, we are basically running the second iteration of this and extending this with newer versions of the current tools. We have a statistical analysis of the results online. There's a GUI also for exploration and so on. I will summarize the results here basically with one sentence. On the data sets that we are currently using here, AutoML is not always performing ideally and perfectly. So either we need much more complex data sets to get a more realistic picture, or we are maybe not as good as we sometimes claim to be in papers where we are benchmarking maybe on very few data sets. Here's a second paper that we published roughly 2 years ago in GMLR. So this addresses the issue that for users it's very often unclear what they should tune, how they should set up the optimization. So of course, if you want to run HPO, you have to define what hyperparameters to optimize over. You have to define the ranges, and it's pretty important for users to get some computationally some computational data-driven ranking of importances of hyperparameters. So what this paper addresses is that it gives a very clear mathematical way of computing that here. It also addresses the question of how to compute optimal defaults for algorithms, and it also gives at least one option for an empirical design of search spaces. So for data-driven computation of bounds for parameters, for hyperparameters. These theoretical definitions in the paper are mainly based, so the theoretical definitions in the paper are also empirically studied. So we actually ran a very, very large scale experiment, also based on OpenML, on many, many tasks, and created lots of different surrogates. And these definitions here that measure how important a hyperparameter is by figuring out how much you can tune this if you basically plug this into an aggregate of surrogates here, and compare this to what you can achieve if you optimize this aggregate. This then defines the tunability of an algorithm, and if you do this for a single parameter, this would define the tunability of that single hyperparameter. A further thing, direction, which is currently, I would say, at least explored a bit more in neural architecture search, but it still should be explored like this, I think, much more, and or used like this much more in also normal hyperparameter optimization. AutoML is multi-objective optimization. So optimizing a model just simply for predictive performance is, in my experience, usually never enough in practical applications. So many tasks you really can't distill into a single metric. This begins with well-known things like receiver operating characteristics, where there's usually always two metrics at play. Discrimination versus calibration problems, and then, I mean, pretty obviously including stuff like fairness, including metrics that measure computational efficiency, either in terms of prediction runtime, in terms of memory usage, robustness measures, or pretty important also nowadays for practical applicability, interpretability measures. So what we usually do is we then, instead of mapping this to a single criteria black box optimization, we map this to multi-objective black box optimization, and we create Pareto fronts. So users can select configurations in a post hoc manner from the Pareto front of optimal solutions. You can do this nowadays. There are lots of options to do this with Bayesian optimization. This is just kind of a short glimpse of the different techniques that are currently available. In the last 5 years, a lot of stuff has also happened here again. And then for evolutionary algorithms, we were able to do this for, I don't know, the last 15 years at least. They work a little bit better with complex and more awkward search spaces. Bayesian optimization is very known to be more sample efficient also in such a scenario. Here are two applications for the multi-criteria stuff. Let me check my time again. Okay, I guess I have to come to the end pretty soonishly. So this is one paper that we published at Gecko, where we applied this to simultaneous feature selection and hyperparameter optimization in order to create a model which is sparse. So this, which contains as few features as possible, and also obviously, of course, also optimizes predictive accuracy, some well-chosen, well-designed metric of performance. And this was addressed through an evolutionary algorithm and through Bayesian optimization, which acted on a configured ensemble of filters. And this is a second view on this interpretability issue, where we try to quantify model complexity for interpretability. So this is basically based on a Fanover decomposition in a model-agnostic manner for arbitrary machine learning models, where we model first-order effects, where we model interaction effects. So we can quantify the sparsity of the model, we can quantify the interaction strength, and we can also quantify the main effect complexity. And all of these things here basically influence how well we can later on run post hoc interpretability methods on these selected models. This was also mapped to a multi-objective optimization problem for model selection, which kind of gave you a Pareto front in the end regarding predictive performance of models and interpretability. I have a few slides for an unfinished paper for explainable AutoML. I guess I have to skip those or leave them out due to timing reasons. Maybe one sentence about this. So in this new paper, we study PDP plots for uncertainty quantification of hyperparameters and recursively partition the search space to get low variance explanation in interesting areas to enable a much better insight into the optimization process for users so they really understand how hyperparameters have been optimized and how reliable these results are when we run IML or XAI techniques on AutoML in a post-hoc fashion. I hope I'm not totally over time. Thanks a lot. This concludes this tour de force. I'm open for questions.
Yes, thank you very much for the great talk. We have a lot of questions from YouTube and also from Daniel, so maybe we can do that one first.
Okay. Daniel, you are muted if you're already asking.
Yes, I was muted, sorry. Thank you for the nice presentation, Bernd. One question from my side, and that touches on your very last slide. My understanding is the idea of AutoML is kind of to automatize the machine learning approaches for data analysis. But isn't there a clash with explainability in the sense that the more you make things automatic, the less they become explainable? Is that invariably so? Or is there like a contradiction?
Yeah, the problem is even they are twofold, I would say. So interpretability needs to be addressed on two levels. So this is in a certain sense, this was talking about this first level. This is selecting a model that is interpretable. So because if you only optimize for predictive performance, what we usually produce is a super overcomplicated model at the end. You have to kind of squeeze out the last epsilons of performance. So current tools often create, I don't know, stacking models or something like that. They're not even, they are not only super uninterpretable, you also have a high technical dependency stack now as a burden. But the second problem is that the process, how these models are selected and constructed, users are not going to trust that if they don't understand that. And there's a lot of current work of trying to do something like that, but people at the moment, at least in my impression, at least, I don't know, normal users are kind of blindly applying interpretability tools also to AutoML. And what this paper, for example, studies is that there's a clear sampling bias, and you can't just easily apply these methods out of the box. And you have to be somewhat careful. But we need to address this issue. We can't just, I don't know, ignore it.
Okay.
Okay, so there's a different question from YouTube, but doesn't these methods require tons of computing power to find the optimal model? How can we minimize that?
Well, first answer is yes, but I guess usually, the question is, do you rather want to spend this time yourself as a human, or do you rather want to, I don't know, delegate this to a machine? And the answer is basically this here, right? Choose a very efficient approach. At the moment, we have become pretty good at that. And the other question is, what is the alternative? And do this yourself in a manual trial and error loop. Don't exploit at all. Another option is basically this here, right? So try to transfer as much as you can from similar problems. And this is still hugely exploitable in my opinion. Yeah, we're getting closer to getting good approaches here. Yeah.
Yes, true. Okay, maybe one quick question. How would one optimize over categorical inputs like PCA versus no PCA in a more efficient way than just trying all combinations?
Well, okay, this is somewhat of a technical question. I'm not sure whether I can answer that so quickly. You basically have to address two things. So one is how you represent that in the surrogate model. This is usually nowadays no problem. Either you use something that's tree-based that can handle that as out of the box, or GPs have also been extended in many, many different variants for exactly that case. And then you can run a then you have transformed the expensive black box problem into a cheap black box problem. And you can, for example, run something like an EA on that, and with a much, much higher budget. That's one, I would say, easy to explain approach, yeah, but I can now cover in 30 seconds.
Okay, sure. Great, thank you very much.
Thanks a lot.
We're gonna move on to the next speaker. Oh.
Yeah, I will stop my screen share and mute myself.
Okay, so our next speaker is Cordelia Schmid. She's the research director at INRIA. Can you share your screen?
Can you see the screen?
Yes, but I cannot see your video yet. I don't know if you're planning to use it.
Well, I was planning to use it, but somehow it just... Okay. Let me try to put it on again.
Ah, yes, now it works.
Okay, great. Somehow it's not. Okay, good. Shall I start?
Yes, the floor is all yours.
Okay, let me know if you don't see the slides or can't hear me. So today I'm going to talk about large-scale learning for multimodal videos. So as everybody knows, there's an increasing amount of videos is available and is growing daily. There are videos on movie channels such as BBC and INA. There are 30,000 hours of video uploaded every hour to YouTube, and there are more than 700 million surveillance cameras worldwide. And so what we want to do, first of all, we would like to classify short video clips in activities. So for example, here, find video clips of birthday parties, or some people are also interested in grooming an animal. And these two examples are part of the multimodal event detection challenge in TrackVid. Another example is text video retrieval. So given children playing football, you would like to find clips, video clips of children playing football. And then finally, the real task we would like to solve is to completely describe the story of a video, that is to really understand who is doing what and why. So for example, here, as the head waiter takes them to the table, they pass by the piano and so forth. So why do we need a multimodal video representation? To precisely understand the video content, you need to have access to all modalities simultaneously. If you look at the video on the left, we can see that the man is serving food to the woman. However, only if we have access to the audio, we understand that the food is Indian, as the woman is asking, is this Indian? And the man answers yes. Another reason why we want to use multimodal video representations is that this is a large amount of weakly supervised data. So we can do large-scale cross-modal supervision with no additional annotation. And so here I show an example of the how to 1 million dataset, where we have video clips and transcribed speech with automatic speech recognition. And for how to video clips, this is in many cases a description of the video content, which we can then use for cross-modal or weakly supervised learning. I'll start by introducing our recent model, Video Bird, then show a recent example for cross-modal supervision, and briefly touch on a video transformer. Video Bird. The idea is to learn from multimodal video. Here we have the video and the corresponding speech transcribed by ASR. So for example, here you can see the example, but in the meantime, you're just kind of moving around the cake. The BIRD model then learns the correspondence between video and speech, and it can learn from large-scale data. A very brief introduction to the BIRD model. What it does pre-training by masking out language tokens or the prediction of the next sentence, and then the model is fine-tuned. Inside the BIRD model, there's the transformer, and in just one slide, what does the transformer do? It can model text, images, videos, which are expressed as sequences by self-attention. And what's the strength of the self-attention? That it looks at the correlation between all the input tokens, instead of just restricting the view field to small neighborhood, as is the case in convolutions, for convolutions. So our video BERT approach builds up on this BERT model. Instead of just taking as input text transcribed by ASR, it also takes as input small chunks of videos, which are described by video features, 3D convolutional features, and then these features are clustered. So here, this is a true multimodal transformer. We use mask language modeling as in BERT, but here, simultaneously for the words and the video clusters, and the video representation is based on 3D convolutions for 1 second time intervals and clustering, which discretizes our features into vocabulary, as is the case for language. Our model is trained on 300,000 cooking videos. We can see an example on the left, and we can see that the speech transcribed by ASR describes the content of the video. Here, keep rolling tight and squeeze the air out to its side. We can then use the model for zero-shot prediction on previously unseen video clips. These examples here on the right, and we see the corresponding predictions make and the verb make and the noun pizza. If we look at the results in a quantitative manner, we can see on the left that if we evaluate our results on the UCOOP2 dataset for verb and object prediction, we can see that our video BERT model, which hasn't had access to any supervised training data, performs on par with a supervised approach trained on the same 3D convolutional input features. So this means that video BERT learns video language correspondence, is close to fully supervised accuracy. And if you look at the table on the right, we can see that actually the pre-training size matters significantly. You can see that the more data we have, the better the performance of our model, and it's not saturated yet. Another example, we can use this model for fine-tuning on the UCOOP2 dataset, and again, we can see that it outperforms the supervised approach, which uses just the same convolutional features. A second approach for cross-modal supervision tackles the problem of zero-shot video question answering. So here, we want to, if we have a question, we want to get one step further. If we have a question, for example, what type of animal do we see? We want our model to predict the answer fish. While this problem might seem slightly artificial, it's actually a good way to see if our algorithm understands the content of the video. We have automatically generated a large-scale video question answering dataset automatically by cross-modal supervision. We start with the how-to 1 million dataset with ASR captions. We then use a textual question answering training corpus for which people have annotated for short Wikipedia data paragraphs, possible answers and questions. Given this corpus, we can train a transformer model and then use this transformer to predict question and answers for the corresponding videos. So what we have now is we have small video clips with ASR, and given this ASR, here the sound is amazing on this piano, we can generate questions such as what kind of instrument is the sound of, and the answer piano. So you can actually see that many, if you evaluate it quantitatively, we can see that half of the generated questions are correct and relevant for the video content. The architecture which we use to model, to learn the relations between your video question answers, again, builds up on a multimodal transformer. We model the video and the question with a video question transformer, and the answer with a simple BERT model. And then for training, we use the masked language modeling loss. And more importantly, the contrastive loss. The contrastive loss measures the difference between what it makes. It wants to make positive answers closer than negative answers. So it measures the contrastive loss between positive and negative answers. And such a loss can deal with large-scale data. Here we have 16 million different answers. A couple of results. Here the question is, so this is, now the results are given for the test set of existing data sets, so we can actually evaluate them. And so here, but trained fully automatically. And so here the question is, what is the man cutting? And our answer is a pipe. If we would only use the text-only response, it would be onion. Because basically most people in these cooking videos are cutting onions. And the next example, what is the largest object at the right of the man? The answer here of our approach is wheelbarrow. If you would use text only, the reply would be statue, because apparently people in many cases captured next to statue. So here again, we can see that the visual information helps to reply correctly to the question. Another interesting finding which performs what we have seen before is that if we increase the training data size, we can see that the performance for zero-shot learning increases. And we can also see that we can use our model as a pre-trained model and then fine-tune it on existing data sets. So in the middle for the zero-shot, we just use the test set, and in the column on the right, we use the training and the test set. We can see that the amount of pre-training data impacts the performance, and it's not yet saturated. And just very briefly, comparison to the state of the art shows that our approach with pre-training in this manner outperforms state-of-the-art methods without pre-training or with other types of pre-training. And very briefly, to conclude my talk, we have also shown that we can extend the transformer approach to characterize videos. And ideally, we would like to integrate this approach in our cross-modal transformer. And here, the idea is to extend the video transformer for static images to videos. And to handle the large number of tokens, we have explored different factorization approaches. In the interest of time, very briefly, here, what we use, we don't use 3D convolutions, but 3D tubelets, use 3D tubelets as input to our transformer. Transformer outputs a head, which is then used for classification. This is quadratic in the complexity of tokens. And to decrease the complexity, we can actually factorize our encoder in first processing the spatial information and then the temporal information. If we look at the results, we can see that spatial temporal models are better for large data sets. The factorized encoder is faster than the spatial temporal model, and it's better for small data sets where we don't have a lot of training set data. We can also see that our spatial temporal model outperforms average pooling. Again, our approach outperforms the state of the art. And in conclusion, we can see that multimodal transformers can model jointly video and text. They can do weakly supervised learning to exploit the large amount of data available online in a way that wasn't possible previously. They rely on the correlation between multiple modalities, for example, video and language, but they're not restricted to those two modalities. And we have seen that it's important to take into account spatial and temporal information when modeling videos. As future work, we want to extend this type of approaches to learning visual representations by interacting with the world via embodied agents. On the left, you can see such an approach where a transformer architecture actually allows to remember things where we're seen in the past. So on the left, we can remember objects which we have seen 50 time steps back. And We have also developed recently an approach which can leverage the large amount of data online to learn jointly better visual representations of houses. Thank you for your attention.
Yes, thank you very much for the great talk. I'm gonna maybe start with a quick question. So the videos you showed are often, I mean, probably obvious because this is kind of EDA videos where it's really obvious where like the center of the attention should be, like there's only one thing happening in the video. What happens if you have videos where there's multiple things going on?
Well, I mean, the videos which we are shown here, they're actually collected automatically from the internet, right? So basically, they're like realistic videos, right? They're not handpicked or anything, first of all. And then second, I would say if there are multiple objects, I mean, if you have, that was actually the last point, if you have a better spatial temporal localization, then you would be able to attend to these objects and it would be possible to model really multiple objects. And one thing we're looking at is actually to see which objects the attention is focused on, right? If you have this attention objects, it would be nice to see now if this model really localizes the fish correctly. So this would be basically the next step, is to see how it localizes the objects and then also check if it works, if multiple objects are present. And one problem is obviously the data sets, right? Because the data sets we're currently using, they're all the state-of-the-art data sets. And so to go further, you would have to have better data sets where these models, where multiple objects appear, right?
Yes, thanks. Okay, so then we have some questions from YouTube. Do you think vision plus language is a good way towards explainable AI? So the model could provide both a prediction and an explanation.
Yeah, this is actually a very good suggestion. And I guess the fact that you have the language, you can at least get an idea what's going on, right? So if you have an explanation from the language and a matching of the language to the vision, it could give you an explainable AI. I mean, we're not there yet, but it could be a way of doing so.
Okay, so another question. If my understanding is correct, both of the models are encoder only. Did you try encoder-decoder models?
Yeah, so basically here we use encoders because we don't want to generate any sentences, right? Decoder models are only necessary if you want to generate sentences. So yes, we have done work where we want to actually do video captioning. It's actually some ongoing work where we want to have video captioning, and there you need a decoder to generate the sentences. But in other cases, you don't actually need a decoder, right? You need a decoder only if you want to generate sentences, and then basically the difference between encoders and decoders is also very, very small, right? A decoder just rolls out things, but basically in many cases you can actually replace the decoder by the same architecture as an encoder. So we have some work on segmentation where we can actually replace the decoder by the same architecture as a decoder.
Would probably also be interesting to generate a video from text, right?
Yes, definitely, but that's very hard, right? So if you have a text, then to generate it in a coherent manner, it's very hard. And what people are currently doing is they're doing this short clip prediction, and even the results are getting better, right? Initially, they were basically more or less random, but now basically, at least for a very short time interval, you can predict what's going on. But if you have a sentence, you want to really generate a lot longer clip, but this is definitely something which is very interesting to do.
Yes. Okay, maybe one last question. The video text relationship in how to 100M is very noisy. Do you actively deal with the noise or do you just live with it?
So far, we're only living with the noise. We have done some manual qualitative evaluation for small data sets. But one of the things what I'm actually thinking of is how to improve the quality. And one future step could be to leverage text data like Wikipedia articles, which describe actually what's going on, and use those to prune out incorrect sentences.
Okay, great. Yeah, thank you again. Then let's move on to the next speaker, which is Henry Schitzer from LMU in Munich. And he's going to talk about humans learn from task description, and so should our models. Are you ready to screen share?
One second.
Sure.
Can you see?
Yes, I see your screen.
Maybe full
Okay,
screen.
so I can go ahead then.
Can you try to put it in full screen? I don't know, Control L or something. Maybe it depends on what program this is. If you go on.
Maybe on view.
Unfortunately, somebody is mowing the lawn here, so I have to close the window. Okay, can I start?
Yes, can you try to put it on full screen? Is that possible? If you go on view, maybe?
No, I don't think that's actually possible because I'm using software to be able to use my pencil on this computer,
Okay.
and I don't think it allows me to.
Never mind, it's good, I think.
Yeah, sorry about that. I should fix that. Okay, then I will go ahead. So the title is Humans Learn from Task Descriptions, and so should our models. And this is joint work with Timo Schick, one of my PhD students. So the question I want to start with is, how do humans learn? And a pomegranate. Let's look at a typical example of human learning, how to open a pomegranate. So before you can eat it, you have to open it. So how do you open a pomegranate? And so in the long version of this talk, I usually show a YouTube video, which is a nice illustration of human learning. In the YouTube video, an instructor shows you how to open a pomegranate. And here you see the instructor, and the pomegranate and the knife that obviously you need. And so the instructor gives a description of the task. We want to open the pomegranate in a way that's not messy and that's not a pain in the butt, because there are, of course, ways of doing it that are really messy, and you get stains all over the place. And a description of how to solve this task. You basically have to, and the method that's introduced here is you score the pomegranate along the ridges with a knife. And that's what you see in this picture. And 3 training instances are given for this process of scoring the pomegranate along the ridges. So I would say that this is a typical form of human learning. You have a detailed description, and you have very few training instances. In this case, just 3 training instances. Now, of course, there's many different types of human learning. This is not the only case, but very often when humans learn, there is somebody there who already knows how to solve the task, and they provide information in terms of descriptions. So this is very typical for human learning. Contrast that with our typical machine learning setup. We have no descriptions in most cases, with a few exceptions, and we have very large training sets, with the exception of few short learning. So the motivation for our approach is humans take advantage of task descriptions. Our machine learning models mostly don't right now. This is specifically a problem in few short learning, because in few short learning, you have very little information to go on. And so you should take advantage of whatever additional information you have. And descriptions are such a source of additional information. And so our question is, how can task descriptions benefit machine learning? One success story in natural language processing in this regard is GPT-3. So I will spend a few slides on GPT-3 because that's important prior work. GPT-3 is a transformer-based language model, a very large model, pre-trained on a very large corpus. And Cordelia already introduced the transformer, so I won't say more about the transformer here. The key innovation is of GPT-3 is that no supervised fine-tuning for a specific task takes place. Instead, what you do to train to apply GPT-3 to a particular task is what they call in-context learning, and I will refer to that as priming in this talk. The priming input to GPT-3 consists of a task description, a few training instances, and a close question. It actually varies from task to task, but I will, in this brief talk, I will only talk about this case. So here we have an example. Here is the task description, translate English to French. Then we have 3 training instances, thanks, merci, hello, bonjour, mint, mort. And then we have a close question, cheese, and the language model is supposed to provide the correct French translation, fromage, here when it is prompted to do so. So there are no parameter updates during this priming. So the language model simply reads this left to right or top to bottom, depending on how you want to look at it. It just continuously reads it, and of course its state changes, but there are no parameter updates. It doesn't do any real learning. So no real learning, you could argue, takes place for a specific task in this GPT-3 approach. Let's look at how important the task description is in GPT-3. And they refer to the task description as the prompt. And what's compared here is using a natural language prompt versus not using it. And you can see that the gap is pretty large, at least for one shot, if you only have a single training instance. So if you have a very small number of shots, then the task description actually buys you a lot. Of course, if you have a lot of instances, then there's no difference between using the task description versus not using it. That's to be expected, and that depends on the task, on the particular setup you're using, and many other things when you get to that point where the task description no longer helps you. But in the beginning, if you have a very few shots, then it certainly does help you. So let's look at the role of supervised learning here. So arguably, humans do parameter updates when they learn. For example, you don't start from scratch when you open a second pomegranate a day later. So in the long version, I show this YouTube video. So imagine you watch a YouTube video about how to open a pomegranate today, and then tomorrow you actually want to open a pomegranate. You have learned something from that YouTube video. You have retained some knowledge about how to open it, and you can use that knowledge the next day. So you have done parameter updates. You've learned something. In contrast, GPT-3 arguably doesn't learn anything after the completion of retraining. So metaphorically, if you show the YouTube video to it today, and then you give it the pomegranate tomorrow, it starts from scratch. It knows nothing about how to open a pomegranate. So our very basic idea is, why not use both the task description and supervised learning, which is what humans do. And that leads us to our method, pattern exploiting training, PET. So I'm going to use this abbreviation here, PET, for pattern exploiting training. And let me explain it for an example task, for the task of sentiment analysis. So given is a review, a restaurant review. It has a gold label, which is 1. The meaning of that is it's positive. So we have a training instance here. The review, excellent pizza, is positive, has the label 1. The first component of pattern exploiting training is the pattern. We define a pattern for each task, or several actually. You can think of the pattern roughly as a closed question. So here's an example pattern: review, it was mask. So review is a variable where we substitute the review, and that way we get a filled-in pattern like this one: excellent pizza, it was mask. So that is the first component of pattern exploiting training. And the second component is the verbalizer. It associates mask substitutions with class labels. So for example, in our sentiment analysis task, we have these two labels, 1 and 0, and the verbalizer associates the label 1 with the word good and the label 0 with the word bad. Here, good and bad are label descriptions. So the task description here is mainly in the form of label descriptions. This taps into the masked language model's pre-trained knowledge of the task. And what I mean by that, I can best explain with this example here. The masked language model probably knows that excellent pizza, it was good, is a lot more probable than excellent pizza, it was bad. This here is a coherent discourse. Excellent pizza, it was good. This here is not a coherent discourse. Excellent pizza, it was bad. And that's the type of thing that language models learn very well. They learn whether something is fluent or coherent, and so they can distinguish these two sentences very well. And notice that this is true in the zero-shot setting. When you don't know when the language model has not been exposed in any way to the task. So there's no training in terms of sentiment analysis yet. But it already knows about the task implicitly because it knows this. So the basic idea of PET is we link elements of the task to natural language expressions. And since the language model has learned about the natural language expressions, it actually knows something about the task through this linking, and that can then be exploited to get better performance in few-shot learning. And this linking between elements of the task and natural language expressions in this case is this verbalizer linking between the word good and the label 1 and the word bad and the label 0. Here's an overview of how the entire process works. So we start with a training instance, excellent pizza 1. Then we use one of our patterns, review, it was mask. We fill in the pattern, a review is filled in, we get excellent pizza, it was mask. This is then the input to the MLM. And the MLM can then predict the words that we have associated with the labels given the mask. So the question is, how likely is each of the possible label words as a substitution for mask? And that's what a masked language model does. It gives us these probabilities. So now we have a probability distribution by back associating it with the labels of the task for the labels. And the supervised learning can happen now. We can fine-tune the MLM on this output simply by using cross-entropy and the training instances that we have. And then in each iteration, the masked language model is going to get better at using this particular pattern and this particular verbalizer. So that is the basic idea of how pattern exploiting training works. So just a brief summary of our experimental results. So PET always works on top of a language model because it fine-tunes the language model. It uses supervised training on the language model. And the one we're using here is Albert XX large. Albert XX large has a size of 223 million parameters. And we're going to compare that with GPT-3. GPT-3 has a size of 175 billion parameters. So if we take GPT-3's size as 100%, then PET has a size of 0.1% compared to that. So we have here a comparison of David and Goliath. PET is David and GPT-3 is Goliath in terms of size. Okay, and here's the comparison, the experimental comparison between PET and GPT-3 on the superglue benchmark, which is one of the frequently used benchmarks in NLP. We're training here on 32 training examples, and we're comparing these 4 systems, GPT-3 MED, which is a form of GPT-3 which has the same size, roughly the same size as PET, GPT-3, and PET and iPET. I didn't have time to talk about iPET, but it's basically a version of PET that in addition uses unlabeled data to get even better performance. If you just look at the average, then we see that, so this is the result for GPT-3, 73%. This is the result for PET, 74%, and this is the result for iPET, 77%. And you can see that PET is outperforming GPT-3 on this benchmark, although it has such a small size. The reason for that is that it combines the power of task descriptions with the power of supervised learning. So supervised learning is, of course, something that you want to use here. It's not just due to the fact that GPT-3 in principle can do that, also because if you reduce it to the size of iPET, then you get a large decrease in performance. So GPT-3 only works if it is really huge, and it doesn't work very well if you use a smaller version of it. Okay, that's basically already my talk. So I think what's really interesting here in the broader context of the MCML and machine learning is the potential of descriptions, which I think has not been tapped yet in machine learning. Task descriptions in PET are pattern verbalizer combinations, where the verbalizer provides label descriptions mostly. What is key is that the method exploits the MLM's understanding of language descriptions for understanding solving the task. This gives the method a head start compared to few-shot learners, because we associate elements of the task with natural language expressions, and since the language model understands the natural language expressions, through that association, it already understands a fair bit about the task, and therefore it has this head start in few-shot learning. Descriptions are complementary, so far little exploited source of information in machine learning. And I think it has great potential for the future, maybe also in fields beyond natural language processing. So I think this might be interesting for many people attending today the workshop. Okay, I'm not sure how I'm doing on time, but that was my last slide.
Okay, great. Yes, thank you. I think we have time for a few questions, and maybe I can start. So how robust actually is this against, I mean, natural language is really flexible. You can say the same thing in very different ways, and also in very complicated ways. Is this relevant for the performance?
Yes, it definitely is relevant for the performance, and it's a problem we have generally in few-shot learning. So if we assume that few-shot learning is an important setting and that we want to solve it, then that's just a general problem, that if you have a very small training set, then the variance is going to be very high, and that's something that we investigate. So if you, as you in this experiment here, as you vary the particular set of 32 training examples that you pick, you get quite a big variance. But we actually make that better through the task description, because it gives additional information kind of regularizing information, and therefore the variance is reduced. So I think what you're describing is a general problem for few-shot learning in natural language processing, but it's something that PET actually partially addresses.
Okay, good. So there's a question from YouTube that's kind of similar. And have you tried using PET versus GPT-3 on non-literal language like ironic statements?
Well, my personal opinion is I'm not aware of any work on specifically non-literal language as far as GPT-3 is concerned. But I mean, that's a general problem we have in natural language processing right now, that non-literal language is very hard. Because you need to tap into things like some basic understanding of the world, understanding about the intentions of people, understanding about typical common sense knowledge, like, you know, how people interact with each other and what typical scripts are, like, you know, the classical examples, like what happens in a restaurant and so on. And that's something that our models right now have a very weak grasp of, if any grasp at all. So we're not addressing that in this work, and that's a big open problem in NLP, but I haven't addressed that today. I have to say very honestly.
Yeah, well, I guess this is also a problem for people sometimes, so it's definitely hard.
Yes.
Okay. We also have a question from Christian Kersting. Can just talk.
Hi, thanks for the talk. So I have a very specific question. So first of all, I was wondering about your opinion. Can we make use of PETs also to connect maybe probabilistic logic programming or logic or general knowledge bases with these masked language models? Because somehow I feel like we can maybe have verbalizers for logical rules, and then within the proof, so to say, if I can't find anything in my knowledge base, I may ask the language model as a starting point. So that's the first question. And the second is, would you be interested in working together? We were making use of masked language models to see whether there is a kind of moral dimension in GPT-3. And there seems to be. We get pretty good results also for detoxification. But I think it would be great to put a bit of supervision in there using the normative data sets due to Riedel and others. And so these two questions in a sense.
Yeah, so I mean, there is work on at least using this approach for, I did dozens of papers on this, so and I haven't had time to talk about these. But there's definitely also work on knowledge bases, using patterns for knowledge bases, and patterns seem to be very useful in extracting the knowledge more efficiently and more exhaustively than if you just use one or two handcrafted patterns. Mm-hmm. And maybe that's also true. I haven't thought about this question if you go to logic. And so my understanding is if you use the wrong pattern, then it may look like the language model doesn't understand logic, but maybe it would, if you ask it the right way, maybe you see that it does have some understanding of logic. So I think that looks very promising to me to do that. And detoxification, I mean, we have our own approach to detoxification. And in principle, I would be very interested to collaborate on that, although it might be best if we do that through Timo, who currently is on an internship. So then this would have to be postponed by a few months.
Yeah, or we can start already on my side. Let's see. Let's just have fun.
That's a very interesting topic, and yeah, we are very interested in that. Yes.
Thanks.
Okay, great. Then thank you again for your talk and for the great discussion. We will move to the next coffee break, which will be until 11:30.
Welcome back to the French-German Machine Learning Symposium. It's my pleasure to introduce our next speaker, Chloé Azencott from Paris, the Mines ParisTech and Institut Curie. Chloé, the floor is yours.
Thank you. So I will share my screen. All right, so now you should see my screen in full screen. Okay, so yes, hi everyone. It's a pleasure to be here this morning. Thanks for inviting me. Of course, as everybody else, I wished I had been in person in Munich, but it's still nice that we're able to meet this way. So yeah, what I want to talk about today is feature selection in high-dimensional data motivated by genomic data. And the type of problem I'm interested in is the following problem: is a setup in which you have a number of samples. So here there are people for which you have a phenotypic information. So that's something you observe at a high level. So here it's binary output vector. So people are either blue or orange. So in a sort of case control study. And you also have a number of measurements for each of those samples along their genomes. And the goal of the work I'm presenting here is to identify genomic features. So along all those features, the ones that I've highlighted in yellow, which are the ones that explain the phenotype. So you can do this type of work on lots of different data types, and I will talk more specifically about a data type that's called single nucleotide polymorphisms, or SNPs. What matters here is that those are features that are along the whole genome, and it has this commonality with any other type of genomic measurement you're going to do, is that you'll tend to have orders of magnitudes more of those features than you have samples in your data set. So here I'm in a high-dimensional, low sample size framework, sometimes called large P small n, which is fairly different from the things you encounter in many big data applications. And that's the setup in which I want to do inference. So the classical approach is basic statistical tests, where you're going to perform a statistical test of association between each of your features individually and the phenotype. And this results in the type of plot you see here in the middle of my screen, which are called Manhattan plots, in which you have on the x-axis your positions organized in the order in which they appear on the sequence of each of the chromosomes, and also organized by chromosome. And on the y-axis, you have a level of, you have a measure of significance here, minus log 10 of a p-value. See, so the highest you are and the smallest your p-value. And you put a threshold at the significance level, corrected for the fact that you have many hypotheses. Here, don't for any correction. And you find that there are some regions of the genome that are associated with your phenotype. So this approach, which is still our mainstream approach in genomics studies based on SNPs, is fairly limited for several reasons. The first one is that because of the large number of features with respect to the number of samples, you lack statistical power. And the second is that, as I was saying, you perform those tests on features one after the other independently from each other, and so you cannot access information that would come from joint contribution of the features. Okay, so what I want to talk about is how you can incorporate prior knowledge that you have about the structure of your features to help improve this situation. So what I'm talking about here is making the assumption that the relevant features are likely to respect a given structure. So what I often talk about is this first example where you are given a biological network, so which comes from all sorts of knowledge we have accumulated about genomics. The edges represent known relationships between the features. And you make the assumption that the feature you select should be connected on this network. And so you can formulate this feature selection problem in a number of ways. In essence, a lot of those come back to using graph-based constraint on optimization problems. So this is just a regularized minimum empirical risk minimization where this omega constraint contains information about the graph. So we've done some work on that, but that's not the work I want to focus on today. What I want to talk about is the setup where you're going to use the hierarchical block structure of the genome. So here what I'm talking about is that generally you're actually interested in some genomic regions and not specific features. So SNPs are like single positions in the genome, but typically you're more interested about whether a gene or another genomic region is associated with your phenotype. And those regions of interest can be split into blocks of correlated features. So here I've split my region into 5 blocks. What I want to talk about here is finding whether this genomic region is associated with my outcome through the association of a subset of those blocks, here highlighted in orange. So for people who are into genomics, those blocks would be called LD blocks. LD stands for linkage disequilibrium. If you're not, just know that there's biological reasons for features that are next to each other on the genomic sequence to be highly correlated. Okay, so what I'm talking about here is a 2-step approach in which our first step will be a selection step in which we're going to select some of those blocks. Maybe none will be selected to carry the most of the signal of the association of the entire region. And the way we perform this selection step is through something that I will call a quadratic kernel association score. So I'm trying to be as generic as possible here. So the score has a form y transpose q of k y. So y here is my phenotype. I have n samples. And k is a kernel matrix that is based on the feature of block k. And I can apply a transformation q to this kernel matrix. So this is not something I just pulled out of my hat. It's motivated because it's a formulation that captures a number of existing propositions, including one that comes from genomics, which is a scat test statistics in which q is simply the identity. And H-seq estimators, so Bernhard Schölkopf independence criterion estimators. So with 2 classical estimators for H-seq, if you have heard of them. And they can both be formulated as such a quadratic kernel association score. So the idea here is that we allowed quite some flexibility through the fact that we're using kernel here instead of the linear scores that are more classically used. Okay, so you can, once you have a score for scoring each of your blocks, you can use several simple procedures to perform selection based on the scores. Like saying I'm going to keep the 10 most associated, the 10 blocks with the highest scores, or something a bit more evolved, but that's would be the idea. Okay, so now the question you have is a question of performing inference and of determining the association between the block and the phenotype, accounting for the fact that you have selected this block. And to illustrate on a simpler example where I'm going with that and why I need to account for the selection event, if I go back to some of the most simple statistical tests where you observe, you'll compute a test statistic that is normally distributed. So that's what you see here on the graph below, the distribution of your Z-score. And if your significance level alpha is 0.05, then the critical value, so the value above which you say that you are significant, is, so if your significance is 0.05, the critical value is 1.96. And if my Z-score is larger than 1.96 in absolute value, I will claim significance. Now, if I'm performing selection and that I'm only keeping the highest Z-scores, so here, for instance, numerically, I'm going to keep only the Z-scores that are in absolute value larger than 1. This moves my statistical significance level because, of course, given the fact that I'm only observing Z-scores larger than 1 is influencing the fact that, yes, my Z-scores are more likely to be larger than 1.96. And if you do the computation, you'll see that you have a significance level at 0.05. Now your threshold needs to move from 1.96 to 2.51. Okay, so here that was what happened on this simple z-score. And now, instead of having a z-score, we have this scoring that was based on kernels. And what we've shown is that if you have a set of kernels, one quadratic kernel association score as I've defined before, and the choice of message for kernel selection of the order of filtering or forward stepwise. The selection event is an intersection of quadratic constraint. And this is similar to a lot of work that already exists in the post-selection inference field, in particular the work of Loftus and Taylor. And having these characterizations allows you now to perform constant sampling, and now you're going to be able to perform statistical testing because you're able to sample the Gaussian variable within this acceptance region here. So depending on your choice of quadratic kernel association score, for some simple choices, you'll be able to do this analytically, but in the general case, that's not true. And you will need an empirical sampling procedure. And so we have proposed a hit and run sampler that's based on ideas that date back from the late 80s to sample efficiently these Gaussian variables in its acceptance region. So to sum up, our kernel post-selection inference procedure allows us, from the genomic point of view, to combine the effect of SNPs within the regions. If we're going to be more general, you combine the effect of feature within a set of features. We use kernel to capture non-linearity, so we can be quite flexible. And the post-selection inference port allows you to obtain valid p-values after selection. So this is work I've done with Lotfi Slim, Jean-Philippe Vert, and Clément Châtelain. And so we have both a paper on the general framework at ICML and a paper on applying it specifically to genome-wide association studies, and in particular including the scaling up of all the computations to be able to deal with this at a genome-wide scale. So to deal with it at a genome-wide scale, we have to use GPUs, and as a side note, we also have implemented HSIC estimators over GPUs. So if you need a fast HSIC estimator, even if you don't care about kernel post-selection inference, you might want to check out this package. Okay, so I just wanted to highlight a few other topics of interest of my group, in the sense that this is about French and German collaboration. So the other thing that I'm interested in, I've already mentioned constraint sparsity in learning on graphs, as well as post-selection inference. A few more things would be stability of feature selection, so ensuring that if I use several subsets of my data, I do get the same features that are selected or the same region of the genome. That helps my interactions with biologists a lot. Also interested in multitask approaches where you have not only one data set, but several data sets with related phenotypes. So I'm emphasizing here that what I call multitask is a setup where the samples are not shared between tasks. And of course, multimodal data. So instead of having one set of features, having several sets of features that represent the genome. And finally, completely unrelated to what I've presented here, I'm also working on causal inference in clinical data. Okay, so this concludes my talk. I'd like to thank people who've contributed to the work I've presented here, in particular, Lotfi Slim for his work on kernel PSAI, and funding in particular from ANR. And with that, I'll be happy to take any questions.
Thank you, Chloe, for the nice presentation. Let's see if we have any questions from the audience. Maybe I'll start with one myself. One of the notorious difficulties from my recollection working with kernel-based approaches is that you always have to choose a suitable family of kernels. And In my experience, typically this aspect is a little bit trial and error in the sense that you try a set of kernels and see how well they perform in one or the other challenge. Do you see somehow more principled ways to figure out what is the most suitable kernel for a specific problem?
So actually, I've presented this work under the light of, it's under the light of using different kernels for different regions. I was performing kernel selection, if you want, using a different kernel for different regions of the genome, but you could also imagine using different kernels for each of the regions you're interested in, or actually in a different setup. Just using just your kernel selection would be about selecting the best kernel, the most appropriate kernel, and not about which other regions it points to. So actually that's one of the things our framework allows, but it still is, of course, you have to provide all the kernels you would be interested in. Another thing here is that in the context of genomic studies, there's some kernels that have been developed specifically for this kind of data. And of course, that would be sort of your first go-to kernels is to use this type of kernels.
Along the same lines, we actually have a question from our YouTube audience asking if you can give us some examples and intuitions behind the most commonly used kernels.
So actually the most used kernel in genomics would be the identical by state kernel. So it's a very simple kernel, but you have to keep in mind that our features, the SNP features, they're the presence or absence of a mutation. So it's ternary because you can have it on two, you have two, strains of DNA, one from your maternal DNA, one from the paternal DNA. So in essence, you can have three values for your feature. And this identical by state kernel is looking at whether on, it's looking at whether or not you have the same value at this particular feature. And if you're doing it not for one feature, but you're using several features, the importance of each of the features is weighted with a weight that's inversely proportional, to the frequency of this particular mutation in the population.
Mm-hmm. One more question, since you've been emphasizing kernel methods here. I remember back 2016, we had a paper at NUREP showing that you can use deep networks for protein structure prediction from amino acid sequence. How do you judge the applicability of deep networks to the challenges that you're working on? Is that doable? What are the difficulties? Is that a lack of training data? What?
Really for me, the issue is first and foremost the lack of training data with respect to the large number of features we're working on, and second of all, I know lots of people, and it's already been the topic it's already been discussed, but interpretability is really, here's the key point, is not so much to make a predictive model as to understand what goes into this model to drive, to help us form biological hypotheses. So there's those two limitations.
Okay. Thank you so much, Chloe. Thank you for this great presentation and the lively discussion. With that, I'd like to hand over to our next speaker, Nicola Ayash, Research Director at INRIA Sophia Antipolis.
Hello, Daniel. Can you hear me?
Yes, I can hear you well.
I can try to share my screen now. Does it work?
Yes, perfect. We see.
Okay, very good. So should I start?
Yes, go ahead, please.
Okay, so first of all, thank you very much for the invitation. It's really a pleasure to be here. And my talk will focus on AI for medical imaging and on the role of models for this. Do you see the next slide? Do you see slide number 2? Yeah? AI and healthcare?
Yes, we see.
Okay, so as we know, AI algorithms allow to augment the reasoning capabilities of the physicians. This is to better take care of their patients. And in particular, it allows to treat an information flow which can be too large and too complex to be optimally processed by a human brain. And this is particularly true to analyze medical images and sometimes with additional data on the patients. And so during the past few years, we've seen outstanding performances of a number of machine learning algorithms, in particular deep learning algorithms with CNNs, and achieving performances comparable to the best expert physicians, sometimes even better. And let me just cite a few examples. It started with in dermatology. It was there shown on mammographies, where Therapixel won this Dream Challenge on 500,000 mammographies. It was shown in ophthalmology, where software was even FDA approved to pose a diagnosis without a physician looking at the images for certain type of retinopathies. And it was the case also in pulmonology for the detection and characterization of a number of lung nodules. So this was shown in this special issue of the Proceedings of the IEEE that was edited with our colleagues Tim Duncan and Michael Insana last year. And even more recently, in this special issue of medical image analysis on the intelligent analysis of COVID-19 imaging data, a special issue edited by Tianming Liu and colleagues, and also in cardiology, where we published recently in Nature Reviews with Maxime Sermezan and Hervé Delingette and two physicians from Bordeaux, a survey on the applications of AI in cardiovascular imaging. So the bottom line of all of this is that this raises really a number of hopes, these excellent performances of deep learning algorithms on medical image analysis. But in fact, it's usually a narrow specific medical image analysis task. Most of the approaches I cited here are purely data-driven approaches that require a large number of annotated databases, and there is a cost of these annotations. There is the issue of representativity. Of course, there are bias. How do we know the bias? How do we take this into account? How do we include rare diseases in these databases? And also ethical issues dealing with sensitive personal data, having some time to enroll controls, and this can be difficult if we are dealing with an irradiating imaging modality. And finally, very often a huge number of parameters leading to a lack of explainability in case of failure, for instance. So a way to overcome some of these problems, not all of them, is to introduce models of anatomy and models of physiology, and to learn the parameters of those models from the patient data to assist diagnosis, prognosis, or therapy. And the combination of purely data-driven or model-based strategies to get more efficient, more robust, more explainable algorithms was very well explained in a paper by our German colleagues, Daniel Rückert and Julia Schnabel, in one of the papers of the special issue I cited, the Proceedings of the IEEE 2020. And so this is to illustrate the digital twin concept. So the e-patient, we have models of the anatomy and the physiology. We have measurements coming from images and other sources. We personalize the parameters of the model, and then we can apply e-medicine algorithms. And this slide is just to illustrate kind of a continuum of models to describe the anatomy. It's essentially based on geometry, semantics, and statistics. And if you want to model the functions, the physiology, on top of this, you have to introduce models of biophysics, biochemistry. And so in the sequel of this short presentation, I will just give some illustrations of both types of approaches from recent research of some PhD students I co-supervised with a number of academic, clinical, and or industrial collaborators. So the first example is in the PhD of Thomas de Marcy. He designed an analytical geometrical model of the cochlea and learned the statistical distribution of the parameters on about 1,000 subjects. And having this geometrical and statistical information available, he could design a Bayesian segmentation algorithm that allowed to extract in a robust and fast manner the cochlea in the image of any new patient, an information very useful for the surgeon. A second example is in neuroimaging, dealing with patients with multiple sclerosis. It's possible to use an irradiating imaging modality, PET modality, with a specific marker to measure the demyelination of the white matter. And the idea of the thesis of Wenwei was instead to use a multi-channel MRI information, use generative adversarial networks that were trained on a number of subjects for which we had both the MR and the PET information, and to learn, in fact, how to predict the PET image from the MR and how to automatically extract this demyelination information. Third example, still in neuroimaging, but for brain tumors. In the PhD of Paweł Mlynarski, he showed that he could exploit again another set of multi-channel MR images with 3D CNNs who have a long-range 2D context and are able to detect and segment the brain tumors. But on top of this, he showed that with other types of CNNs, introducing some anatomical constraints, he was able to segment the so-called organs at risk that must not be irradiated during a radiotherapy. And even on top of that, we showed previously, it was in the PhD of Mathieu Lé, that it is possible with an additional biophysical model of tumoral cell density to estimate the cell density beyond the visible boundaries in the MR images. And with an additional biophysical model of radiotherapy, it's possible to optimize the dosimetry planning. And this type of ideas are now implemented in the companies that Nikos Paragios created recently, Terra Panacea, to really exploit AI and this type of models for optimized radiotherapy. Another example is in cardiology, and in his PhD, Kiao Zhang exploited the UK Biobank, in fact 5,000 MR images of beating hearts, to first extract with a data-driven approach the left and right ventricles in a completely automatic manner. And then, and this is a nice combination, in fact, of data-driven and model-based approach, then he designed a number of handcrafted shape and motion phenotypes, exploiting the segmentation information that could then be injected into very classical and explainable classifiers to detect and characterize a number of cardiac pathologies. Another approach, still in cardiology, was proposed by Julian Krebs in his PhD, where he used the conditional variational autoencoder for 3D diffeomorphic registrations to learn a cardiac probabilistic deformation model between the end diastole and the end systole stages of the cardiac motion. And he showed that the reduced latent space that he learns allows for an easy classification of the previously mentioned cardiac pathologies. On top of this, and this was shown a long time ago already by Maxime Sermezan, it's possible to refine the anatomical model, introducing the cardiac fibers. It's also possible to add information about the vessels, about the scars revealed by contrast agent. And so this is done by the startup company InArt, created between INRIA and IHU Bordeaux. And with this very refined model, it's possible to add an electrical and a biomechanical model to learn the parameters, for instance, to quantify here a heart failure, and even to use the personalized model of the heart to predict, for instance, the effect of resynchronization therapy. And here we see in the PhD of Roch Molero, for instance, within a European project, they personalized up to 120 different patients. So all these hearts have different parameters, electrical and mechanical, that can be used for the diagnosis and also the therapy planning. So to conclude, the trends now, especially from a number of databases that I listed at the bottom of this slide, is to learn from so-called holistic patient data, not only images and signals, but also clinical scores, clinical reports, information about behavior, lifestyle, environment, and also biology and omics biomarkers. And in the PhD of Luigi Antelmi, for instance, it's in neurology to study patients with neurodegenerative diseases. What shows Luigi is that it's possible to use a sparse multi-channel variational autoencoder to learn from heterogeneous data, including structural MRI, PET molecular images with 2 biomarkers, various clinical scores, biological information, to learn in a joint small dimension latent space the important parameters on all these patients, and to do an unsupervised staging of the disease from transverse data from cognitively healthy subjects to patients with dementia and with intermediate stages of mild cognitive impairments. And just to conclude, what Clément Abinader showed in his PhD is that if you have longitudinal data on the cohort, you can introduce a dynamic model in the latent space on a number of explainable latent variables, for instance, related to amyloid deposit, to glucose consumption, to atrophy in the cortex, and to clinical scores, to quantify and to reproduce the evolution of the disease. And what he showed also is that it's possible to use this tool to simulate, for instance, a treatment, reducing the amyloid deposit in the brain. I will not describe these other projects in which I am also involved with partners and with students, but I will just mention that we are also working on the automatic analysis of abdominal ultrasound images. on the analysis of lung digital pathology images, on working on prostate MR images, on bone fractures, and on whole body PET CT. And I will conclude with mentioning that there are, in the Troisia Côte d'Azur, there are other projects involving AI and healthcare, because AI and healthcare is a major application field of this interdisciplinary AI institute. So I'd like to conclude with this slide and just mention that the papers I mentioned are all on our website at the bottom of this slide. Thank you for your attention.
Thank you, Nicolas, for this great presentation and overview. Do we have questions from the audience? Maybe I'll start with a question myself. A lot of the approaches that you've presented tend to be a combination of, say, handcrafted elements and then a learning-based approach. Do you see over the last years and kind of prospectively into the future a transition towards more learning-based and less handcrafted? Can we compensate for missing kind of model knowledge by just more and more training data? Is that a trend that you see there?
Yes, there is clearly this trend, and the first example I showed were really purely data-driven approaches with excellent results. So the combination, in fact, is introducing more knowledge about anatomy and physiology is required when you want to do more than, for instance, a segmentation task or a detection task. For segmentation and detection, it seems to be really the best approach to have a purely data-driven approach with a lot of data for the learning. But when you are in situations where either you have less data, or if you want to go beyond this and, for instance, optimize the dosimetry or predict the effect of a given therapy, then you have to introduce these models of the human being. Somewhere it's reassuring because we know a lot about the human being, and having to introduce this information is sometimes reassuring.
We also have a question from our YouTube audience to Nicolas. The question is, what's your opinion on the trade-off between performance and explainability for AI in healthcare? Like, which one would you think should be emphasized more in the next decade?
It's a very good question, because if you have a system which works perfectly well but is not explainable, what the hell? It has been the case that some medicines were authorized before all the mechanisms were understood, just because they were very efficient. So I think the really key, so the most important thing is really the performances. And if the performances are not sufficiently good to have a non-explainable algorithms, I think the community, the users will ask for explainable solutions.
Okay, so I also have a question. When you build personalized models for single patients, what would you think? So how do you handle, like, so imagine like everyone is different, so you have to adapt to this, but probably you also have noise. So how do you get a good ratio between using the prior information of the average behavior and this special information that you have for the single patient?
So the question is about the ratio between what we learn from a population and what we can obtain for a given patient. And in fact, it's really related to what I mentioned at the beginning, the databases on which we do the training. They have to be as representative as possible of all the situations we can encounter. And of course, if this is not the case, for some very singular patients, the personalization could fail, in fact. And so it's very important to analyze the representativity of the databases on which the training is done.
Okay, thank you, Nicolas, for the exciting presentation and the lively discussion. With that, we'll move on to our next speaker, who incidentally, I think this is random coincidence, happens to be from the same place. Charu Bon, full professor at the University of Côte d'Azur and also director at the PRAIRIE Institute.
Thank you, Daniel. Can you hear me correctly on my slides?
Yeah, you're fine.
Perfect. So thank you very much for this invitation, for organizing this with Jean. It's a very nice work, and of course it's not so easy to conclude such a morning. So my name is Charu Bon. I am a professor on the chair in artificial intelligence at Institut Trustworthy Côte d'Azur. In fact, I am also the director of this institute. So in the line with Chloe and Nicolas' talk, I'm going to present some application of statistical learning with interaction data, but for public health, so at the public health level this time. So let me just first mention some additional thing about after the teaser of Nicolas about Trustworthy Côte d'Azur. So of course you all know the postcard of Côte d'Azur, but behind this there is also an exceptional site for research with top-level research institute on the Côte d'Azur. And thanks to this, we were able to build an ambitious research project for this National Institute Trustworthy Côte d'Azur. So we now have a vibrant ecosystem organized around 4 axes. So core element of AI, AI for computational medicine, AI for computational biology, and also application for smart and secure territories. We have 39 chairs and about 50 PhD students in the team, and perhaps 200 researchers around this. And about core element of AI, I also wanted to mention that we created last year a research team in appointment with INRIA and Université Côte d'Azur, which I am leading. So it's a new team on the model and algorithm for artificial intelligence. So it's a new team to strengthen the French-German collaboration on AI. So about model and algorithm for AI, I just wanted to present shortly 2 models and their application. The first one is about the statistical analysis on networks, and in particular for analyzing COVID-19 publication networks. So we all know that the analysis of networks is now a strong discipline, and in particular in statistics. And we have application to large domain like biology, historical sciences, etc. And it's important also to remind that network can be observed from a variety of sources. You can think about social website, but also numeric document like Panama paper or co-authorship networks. And in fact, something which was surprisingly forgotten by most research is the fact that they rely on text. And this is the topic of this work, is to try to work both on networks and text at the same time. So just to give you the big picture of our work, we consider here a very small network of people exchanging, let's say, email. And what we are quite good now at for years is to make the clustering of such a network. So here we cover 3 communities of people having a similar behavior on the network. And what we would like to do with our approach is to work on data like this. So we observe the edges, but we also observe the text which is on the edges, the text of the email or the abstract or the text of the co-publication. And thanks to with the stochastic topic block model we introduced, we are now able to both cluster the nodes, but also cluster the topics that represent the text. And as you see, we also have a finer analysis because here we were able to split the blue group into subgroups because they have a specific language. So just to give you an overview of this model, so we work with network data that are presented by an adjacency matrix. It's a square matrix where aij is equal to 1 if I sent an email to J. And of course, if aij equal 1 is equal to 1, so we have a set of documents that describe this relationship. So WIG gather all the documents that are shared between I and J. And of course, in WIGD, we have all the set of words that were used by I when writing to J. So here is the model. So we first assume that there is a latent group describing the observation I. So why I is a latent variable which is supposed to be a multinomial distribution with the parameter rho, which is finally the prior group proportion. And here is the model. So for the edges, so we assume that aij, knowing that I belong to cluster Q and J belong to cluster I, is distributed as a Bernoulli distribution of parameter pi QR. So here, as you see, the latent groups, of course, generate the way we connect. So this is what for the edges, and now we have to model also the documents. So here we introduce a theta TQR parameter, which is the vector of topic proportion that people from cluster Q will use for when communicating to cluster R. And once you have this, you can draw the latent topic of the word N document D that I send to J according to a multinomial distribution of parameter theta QR. And finally, you can draw the word in the dictionary, knowing that this word should be in cluster in topic K according to a multinomial distribution of parameter beta K. So you probably recognize a mixture of a stochastic block model and latent directional allocation, which is exactly what we do in this model. So of course, the most tricky part is hidden in the inference. So here we propose a classification variational expectation maximization algorithm for inferring this model. And thanks to an ECL criterion, we were able to provide a fully self-supervised algorithm. So you will find all the detail in the associated publication. So here I just wanted to show an application of this model to a specific case, which is the analysis of COVID-19 publication networks. So it was done with the linkage.fr platform, which implements the STBM algorithm. So here is what we do. We just try to summarize and identify the different topics and communities that are working on a specific topic, here COVID-19. So we use all publication on main archive and bioarchive until last week with this two COVID-19 and SARS-CoV-2 keyword. So as you see, it's quite large network with a lot of edges. And thanks to this, we were able to provide this summary. So this is a meta network, which is provided by the algorithm. So we have a very large here group that gather all small communities that are working alone in hospital on different topics. And then there is some network of people that are well structured and also, as you see, very specialized, because the color of the link between the groups depend on the majority topic which is identified. And of course, we need to now interpret the colors. And here the colors correspond to the topics that we detected. And if you just have a very short screening of this, you will recognize some of the topics that are expected for this subject. And of course, you now have a better understanding of this analysis. So I have no more time to discuss this. So go on the website. The analysis is public, so you will be able to play and to interact with the data. And I wanted also to give another overview of on the clustering of high-dimensional data with a specific application to pharmacovigilance. So, of course, pharmacovigilance is, as you all know, a very important application in medicine. So it's a study of the interaction between drugs or vaccines and adverse reaction. And, of course, it's very important to be able to monitor those data to detect some safety signals in order to perhaps stop a drug. Here we work with some data from the Nice hospital. So as you see here, we have a lot of tables corresponding to each month between 2010 and 2020. In line here, you have the drugs. Here you have, the adverse reaction, and here the drugs. And then we have the count of the number for this month of interaction between the drug and the adverse reaction. So it's a very large data set, of course, because we have thousands of drugs, thousands of adverse effects, and we here work on the 10 years scale. So of course, it's a lot of data to handle. And our approach was to use a model and propose a new model to just summarize this large data set as clusters of rows, of columns, but also of time slices, in order to have a very nice summary of this very impressive data set. So here is the model. So it's quite close to the one we proposed before, but for a different application. So here we have three latent variables, Z, W, and S, for cluster membership of rows, column, and dates. So they are all multinomial distribution with specific parameters. And then we assume a strong assumption. We assume that the number of interaction between the drug I with the adverse effect J at time slice U, knowing that I is in cluster K, J in cluster L, and U in cluster C, is a Poisson distribution with a specific parameter lambda KLC. So it's a very strong assumption, but it leads that the clusters that we should find should be very precise, because they will carry all the important information. And of course, again, the difficulty is in the inference of this. But before, I just wanted to say that on the dynamic, it's very important to understand that a time cluster can come back. For instance, D1 come back here because the period is again on the same level of activity regarding the data. So of course, the inference of this model was again quite difficult, and we rely on an algorithm which is a SEM Gibbs algorithm in order to infer all model parameters, and we rely again on ICL for model selection. So all the details are in this preprint. And here are some results that I can comment. So of course, you see a first impressive peak here, which is recognized as a specific cluster, which is great. So this one corresponds to the levothyrox crisis, which was very popularized by media. But it's very interesting that even though we have this very big peak, we have thanks to a DSBM, recognize some smaller events that are in fact of very high importance on the public health level. In particular, this one, the red one, is related to the Mirena crisis, which was also a very important public health event. And then we have also the purple and the blue clusters that are recognized. They are different than the levothyrox one because those concern generic drugs that were proposed for the levothyrox. And we also have some let's say, basic patterns that are recognized. And we also were able to look at the different interaction. So first, it's perhaps important to notice that cluster 1, 5, and 6 were in fact devoted to only one drug each. So this one was levothyrox, this one was Mirena, and the last one was Mediator, which was a very, of course, famous public health event. And then we have groups that are clearly larger, gathering a lot of drugs. And we did, of course, also the clustering of adverse effects in columns. And thanks to this, you can follow along the different time clusters the way the drugs interact with adverse effects. And as you see here for the levothyrox, we have a dynamic which is very interesting to follow with adverse effects that slightly vary, which is of course very important for medical doctors. So this is just what I wanted to present today. I will just conclude with this sentence from a French poet, and it's a nice summary of my way of looking at statistical learning. And here is a couple of announcements. Thank you very much.
Thank you, Charles, for this great presentation. Do we have questions from the audience? I'll start with a question myself, if I may, just to get the discussion going. This is about the social network analysis work that you've done. I think social network analysis and research is quite fascinating, but how do you feel in general? Is this a problem that is good to be tackled by people in academia? The issue is obviously that, as we know, a lot of the state-of-the-art learning methods, the performance of methods like deep networks scales with the amount of training data you have available, right? And now if you take companies like Twitter and others, a lot of the data that we're talking about is proprietary data, and it's not publicly available. And sometimes you can get chunks of data, but it's typically always very small chunks of the whole picture. And so whatever you develop will invariably not be state-of-the-art in terms of its performance. How do you feel about that? What can be done?
Of course, it's a concern because the network data are not so easy to get, of course. But in fact, as I said, it's in fact possible to recover the network from perhaps documents that are less structured. So of course, it's a specific work to do that. But if you think about the Panama Papers, they did this kind of job. So they have a lot of documents, and thanks to this, they were able to reconstruct the network, and in fact, a large network. So clearly, it's a concern, but I just would like also to comment that even for very large group like the GAFA, analyzing network is not so easy because, of course, as you know, the number of ages grew up with a square of the number of individuals. So it's having even 10,000, 100, it's a lot.
Again, we have a question from our YouTube audience regarding the medical part. The question is, will multimodal holistic approaches that you're advocating not be even more difficult to accept by the medical community?
So here we are talking about really a public health problem. So it's some people that are looking at a high level of the data. So I think it's very important for them to have those tools, in particular for the pharmacovigilance, because it's perhaps not well known, but nowadays people are doing this kind of analysis manually. So clearly having a tool like this could help a lot. And in particular in pharmacovigilance, we have something which is very strange. When there is let's say a large mediatization of an event, there are a lot of reports that are in fact useless because it's about adverse effects that are known. And this is of course very problematic for people in pharmacovigilance because they do that manually. Having some kind of tool could be of course of great help, we hope.
Okay, thank you, Charles. I see there's no more questions. I also see where the time is up. Thanks everyone for also staying in time very much. We're perfectly on the clock. You know, the German punctuality, maybe it actually does exist. Or the French in this case, because
also
in the whole French session now. So thanks everyone for contributing. We now have the lunch break and we'll reconvene in 1 hour at 13:30 with the presentation of Laurent Bezacier. Thank you.
Thank you very much.
Welcome back to the French-German Machine Learning Symposium. I'm happy to introduce our next speaker, Laurent Bezacier from Naval Labs Europe. Laurent, the floor is yours.
Thank you, Daniel. So yeah, I'm Laurent from Naval Labs, and I'm going to talk about self-supervised learning for building speech systems. So I will give a brief overview of self-supervised learning for speech, and then I will share my own experience on using such approaches for building speech applications, and I will finish with some takeaways. So what is self-supervised learning? First, so the idea is to use unlabeled data for training models where the targets are computed from the signal itself. So I quote this very good definition from Chen et al. 2020, where it is said that the idea of SSL is to learn representations using objective functions that are similar to the one used in supervised learning, but the networks are trained using some pretext task where both inputs and labels are derived from the unlabeled data itself. So from the data set. So this has been introduced for vision, and for instance, this work from Chen et al. Learns representation by contrasting positive pairs against negative pairs, and this has been also very successful in text natural language processing. For instance, this paper from Devlin et al., which introduced a BERT model, where representation are learned by predicting tokens that are masked in an input sequence. But so focusing on this NLP approach, this yields to a now very well-known approach for solving some NLP tasks, which consists in two steps. First is pre-training those models on a very large amount of unannotated text, using one or several self-supervised learning tasks. So for instance, for BERT, in the initial approach, two different tasks were used. The one is called mask language model prediction. So you mask a token and you try to predict it from the context. And the NSP here means next sentence prediction. So just to highlight that self-supervised learning can also be multitask. And so once you have pre-trained such a model here, then you can solve the task of interest, for which you do have a limited amount of annotated data. So you just add a specific layer on top of it that will be specific to the task, and then you will fine-tune the full architecture using your supervised data, whether you are addressing question answering, name entity recognition, or different tasks. But what about speech? So traditionally, people have been using uncrafted feature vectors for speech processing. So basically, you will extract very local features on 20 or 30 millisecond windows of signal, and the different kind of features that can be extracted are filter banks or capsular coefficients, or features coming from linear predictive coding. And of course, with the rise of deep learning, learned representation were also introduced, but mostly for supervised tasks. For instance, using convolutional layers in the first stages of the neural network pipeline. So interestingly, self-supervised learning on speech was barely addressed until 2019, even if it's worth mentioning the Zero Resource Speech Challenge, which proposes unsupervised representation learning shared task since 2015. But this Zero Resource Speech Challenge has a slightly different objective, because it appeared and it was introduced by researchers in child language acquisition. So they were interested in representation learning from a limited amount of speech, not from a huge amount of speech, like several thousand hours of corpora. So in this presentation, I will focus on self-supervised representation learning from speech, from very huge amount of data, like several hundred or several thousand hours of recorded speech. So on that aspect, one interesting first approach was proposed by a group at MIT in 2019, and it was called APC for autoregressive predictive coding. And the idea is somewhat inspired by language models for text, because the idea is really to try to predict a future frame given an history of previous frames. Like where you try to predict a token given an history of token using a language model when you deal with text. And for instance, you can this way predict the probability of a sequence, which will be the product over all the tokens given a given history. And this history, for instance, can be modeled by the state of a recurrent neural network. So just imagine that it is very similar to the architecture used for a recurrent neural network language model, but this time, instead of having embeddings of word tokens, you just have directly acoustic frames or acoustic vectors. And there is another difference, which is the fact that contrarily to text, where you do have a limited and final set of target tokens, you don't have that for the acoustic vectors, because this is a continuous, you are lying in a continuous space. So then your softmax layer might be replaced by a regression layer. So in the end, in this seminal approach introduced, the learnable parameter are the RNN parameter and the regression layer parameters. And in order to encourage the model to infer more global structures, rather predicting the next acoustic vector, the model is encouraged to predict a vector that is n steps ahead of the current one. So there is a locate parameter n here that will force the model to learn more global structures. And the model is optimized using by minimizing L1 loss between the true sequence and the predicted sequence. So this was applied to automatic speech recognition in English and speech translation from English with interesting performance compared to a baseline that was based on log-mail filter bank features. So the uncrafted features I've presented so far. And in that case, when you use this approach, what are your feature vectors? So they are just the representation of the RNN hidden states. So at this stage, we can look at a comparison between speech and text self-supervised learning. So the input speech representation are already in a vector form. They can be MFCC or filter banks. So you don't really need an embedding layer, whereas you need an embedding layer when you deal with text to project your token into a large dimension. And in the meantime, there is more uncertainty in speech. So text is discrete. So as I said already, you have a finite number of possible outcomes, which are the target tokens. Whereas when you deal with speech, and this is also true for video, you have an infinite number of frames that can plausibly follow a given history. While when you deal with text, some very efficient methods are based on masked language model prediction, for instance. When you deal with more continuous and data with more uncertainty, contrastive methods might be a good choice. And this is exactly what was proposed after this initial approach based on APC. And this was introduced by a group from Facebook, and the approach was called contrastive predictive coding, CPC. And I'm going to describe this approach a little bit, which is also called wave-to-vec by the authors. So in short, this is so the authors propose a fully convolutional architecture, which is made up of two subnetworks. There is one first subnetwork that will go from the signal X to a local latent representation Z. So this is really the extraction of local acoustic features with a small field of view of 20 or 30 milliseconds. And then you have a second subnetwork from Z to C that will extract more contextualized representations. And how is it done? basically, what is a self-supervised task? So based, for instance, on a contextualized representation at time step I, for instance, Ci, then the goal is to predict if a latent representation Zi plus k, for instance, here, is a true observation, or is it a negative sample, a distractor example? So it's a classification. We just need to decide, is it the true latent representation in the future, or is it a negative? And this will be done for different values of k being the look-ahead parameter somehow. And the average loss will be average over all those values of k. And the negative are just sample from a uniform distribution on the current signal. So this approach was shown to be very efficient for pre-training speech systems. So there were many follow-up in 2020. I go quickly about them. This problem agnostic speech encoder used a multitask framework, so self-supervised multitask framework to build more robust representations. Then also in this speech XLNet approach, so the self-attention networks were used also to build those unsupervised representations. And you may have noticed that for the APC and CPC approaches I have just presented, we were predicting the frame in the future, but you can actually try to predict a masked frame using the left and the right context. So using bidirectional encoders, and this was done with these two, this third and fourth approach mentioned here. The one maybe I want to talk a little bit more about is the last one, which is called Wave2Vec 2.0, which is a significant iteration on top of the CPC approach I have just presented. So let me just spend 1 minute on presenting it here. So remember, for the CPC, we had a fully convolutional architecture with two subnetworks. So you still have those two subnetworks here. You go from X to Z, extract local feature, and it is still done with a CNN. But then instead of, for the contextual subnet, instead of having a convolutional architecture, it has been replaced by the transformer architecture, which is based on self-attention. So this is the first difference. The second difference is that the authors noticed that it was more effective to actually quantize the latent representation from the local feature extraction. So basically here, the representation are quantized, and this is the second difference. And finally, this is predicting if a given representation is correct or if it's a negative, but now not only using the past, but also using the future of the context. So this is also bidirectional. So these are the three differences related to the initial CPC approach I presented earlier. So let me now, for the remaining 7 minutes, share my own experience on experimenting with those self-supervised representation for speech. So the first task I addressed with my colleagues was end-to-end speech translation. So what is end-to-end speech translation? It consists in translating a speech signal in a source language directly to the text in the target language, without actually going for the transcription of the source speech in the source text. So you just bypass the transcription, you go directly from the speech in the source language to the text in the target. And so for training such model, you need some parallel data, speech text in both languages. And this task is somehow low resource by essence, because the biggest corpora you will find for solving this task are made up of several hundred hours of translated speech. So we investigated if using contrastive predictive coding to pre-train a model on large amount of raw speech would help. And by the way, this scenario is very useful if you want to deal with oral languages, for instance, for which you do not necessarily have transcription, but you can obtain translation. So basically, we use a very conventional architecture So our encoder is made up of a bunch of CNN encoder blocks followed by RNN blocks, which were by LSTM. And at the input, we either use the conventional filter bank features, or we use our self-supervised wave-to-vec features. And we apply feature dimension reduction in order to have to keep the same number of parameters in the rest of the architecture. And we also apply or not mean and variance normalization on the feature vectors. And then our decoder is quite standard with 2 LSTM layers, and we use Badano's attention. So if you look at the learning curves in low resource scenarios where we use only 28 or 56 hours of translated speech, you see that when we use filter bank, we cannot really train the model correctly. Whereas using these wave-to-vec self-supervised features, we get better learning curves, and even better if we normalize those feature sequences. Talking about results, so when we evaluate speech translation, we generally use this scores called BLEU, which is the higher the better. And you will see that from our observation here, in low resource conditions with less than 100 hours of translated speech, there is a clear impact of an improvement using the wave-to-vec versus filter bank features. But somehow this improvement goes away if we use bigger corpora. So in other words, our observation here is that this self-supervised learning helps only in low resource conditions. I wanted to mention a second low resource task. I've been working on ASR for 3 low resource languages from sub-Saharan Africa with students from the African Master of Machine Intelligence. And these were very low resource conditions because only 2 hours of transcribed speech were collected. And we had only 1 hour for fine-tuning the speech recognition model and 1 hour for evaluation. So we didn't have access to large amount of raw speech for those languages. So we tried to use a pre-trained model on English. So here the research question was, do those self-supervised models transfer cross-lingually? And the answer is yes. So we pre-trained an English model on 60,000 hours of speech, of English speech, and try to apply it to just add a linear layer on top of it and train the parameters of these linear layers using the 1 hour of transcribed speech we had for the specific language pair, for the specific language, Wolof, Somali, or Ga. And we got some very decent word error, phone error rate for these languages. We also tried to train a model specifically for Wolof, but the data was too small. So basically, it's better to use a big model trained cross-lingually rather than a smaller model trained in the language of interest. So the takeaways of this presentation are that yes, self-supervised representation learning from speech allows to adopt the pre-training plus fine-tuning methodology that is widely used in text, in NLP and other domains. This reduces the dependence on labeled data for building speech systems. And from my experience, this is particularly efficient in low resource scenarios where you have few annotated data available. So this is a very rapidly evolving subdomain. We have already moved from APC, CPC to mask reconstruction models. Some huge raw speech dataset for many languages were recently released. One shortcoming of this subdomain is maybe the fact that there is no shared benchmark to evaluate all these approaches. This is why with some colleagues, we have submitted this paper to Interspeech 2021, which proposed a reproducible framework for assessing SSL from speech. We called it Le Benchmark because it focuses on French language And we have also pre-trained some SSL models based on Web2Vec 2.0 on large amount of French speech, very diverse corpus. And this is made available for the Hugging Face Transformer library already. So this is the end of my talk. I will be happy to answer to some questions.
Thank you, Laurent. Unfortunately, we're a little bit over the time already. So in order to keep to the schedule, I would prefer if we could maybe move on to our next speaker, who is Gérard Biot from the Sorbonne University, and who will be speaking about Wasserstein GANs and some theoretical insights on these. But on the YouTube channel, there may be other questions. So Laurent, if you do have time to visit the YouTube channel, maybe there's some questions.
Sure, I will.
For you. Thank you.
Yep. Thank you very much, Daniel. Can you see my screen?
Yes, I can.
Okay, thank you very much, Daniel. So good morning, everyone. Thank you very much for this wonderful invitation, this beautiful meeting. So the title of my talk is Some Theoretical Insights into Wasserstein GANs. And so thank you to Benoît Cadre from University Rennes 2, Maxime Sagnier from Sorbonne University, and Hugo Tanilian from Criteo AI Lab, who are my co-authors. So GANs are just a means to generate new observations. So on the left, images, on the right, new images, which have been generated by a GAN. And so the idea is to generate new observations which fortunately have not been observed in the original sample. So this is a generative problem. So at a high level, a GAN is made of two parametric models, two neural networks, if you prefer. A generator, which takes as input a random noise and which produce fake observations, images, for example. And these observations are compared to the true observations by a second parametric model, a discriminator. And this discriminator says, or tries to say, whether the produced image by the generator are real or fake. And these observations are passed to, or this conclusion is passed to the generator, which tries to improve its strategy. So that's the basic description of GANs. And in this presentation, I will try to tell you some words about some key math properties which are behind the analysis of GANs. So first, I will start with the general context of GANs. Then I will more deeply discuss the WGANs framework. And finally, I will provide you with some optimization and asymptotic properties. So the math context. So what we want to do is to generate, according to an unknown probability measure, mu star, on E, which is a subspace of R to the D. So R to the D is the space of images, say, and it's of course a big dimensional space. So we want to generate according to mu star, but of course we don't know mu star, and what we know is observations which are drawn RID according to mu star. And the general principle is that we are going to use what is called a latent random variable, which is living on a small dimensional space, R to the small d, so typically dimension 2, 3, or 4, Gaussian or uniform random variable, that we are going to transform by some transformation G, parametric model, say a neural network, which is going to live in the big dimensional space R to the d. And the key, of course, is to analyze this transformation. So the generator, as I said before, is a parametric family of functions which starts from R to the D to E. So it's a collection of parametric functions, G theta. So in practice, it's very often a neural network. And the principle then is easy. We have a uniform or Gaussian or easy random variable, Z, and we transform Z by G theta. So we end up with a collection of probability measures, let's say mu theta. They are the push forwards of the distribution of Z. And so at the end, we have a collection of probability measures, mu theta, on the good space, I mean on R to the capital D. And each of these probability measure is in fact a candidate to represent, to approach mu star. And of course, the question is, how do we select the best measure to approximate mu star? So again, we know Z, it's typically uniform or Gaussian with D small, but that won't play a very big role in my presentation. So for now, I have described the general principle, and I have to describe now what is the generator. So my generator will be a deep neural network, so a traditional really neural network of this form with p-1 hidden layers. So it's a really neural network with so really activation at each neuron. So for the discriminator, it's again a parametric family of functions. This time it starts in the good space, E, in the big dimensional space, and it lands in 0, 1. And the role of the discriminator is to, well, to make the distinction or try to make the distinction between what is true and what is fake. So again, in GAN's algorithm, it's a neural network, but it can be more generally a parametric model. So the idea is that the higher d of x, the higher the probability that x is drawn from mu star, the true distribution. So clearly the generator and the discriminator, they have opposite objectives in the sense that the discriminator likes observations which are either close to 1, they are generated by mu star, or close to 0, they are fake observations, whereas the generator likes observations which are close to 1/2 in the sense that nobody can distinguish whether they are true or false. So these are the generator, the discriminator, and that's where I am here. I have described the discriminator on the top. And in this presentation, I will take a deep neural network again, but with a special activation. It's called group sort activation. So again, it's a deep neural network with q-1 hidden layers. And the activations, it's just an alternance of max and min the neurons. And I will explain why I need to take this type of activations. That's to guarantee some Lipschitz nets properties. It's very interesting to keep this in mind. So now, how do we put into music the generator and the discriminator? Well, originally, it's by solving the following criterion. So for a fixed theta, it means for a fixed generator, then the discriminators maximize this criterion. So it's a sort of likelihood. X is it's just a random variable with distribution mu star. And so this criterion has to be maximum on the d alpha of x, which are the true images, and minimum on the fake images, the d alpha of g theta of z, I mean the distribution which is produced by the generator. So it's a very intuitive criterion. Of course, it's at the measure level, and at the empirical level, we don't see x, we see observations, x1, xn, and so that's the empirical version of the theoretical objective. So the generative principle then is quite easy. Once you have solved this problem by computing some theta n, the optimum of this criterion here, then you have a particular neural network with a particular weight g theta of n. And then, of course, by drawing samples of z, then you can generate as many images that you like. I won't speak today on the min-max optimum problem, which is a very important problem, which is usually solved by alternate stochastic Bredon descent. And of course, 99% of the literature on GAN is devoted to try to have good algorithms in order to compute this min-max problem. Today, I will be more on the stat problem of GANs. So what are in this paysage Wasserstein GANs? Well, if you want to understand what W GANs are, then you have to understand what traditional GANs are. So let me remind you that what we call the Jensen channel divergence between two probability measures mu and nu is just a symmetrized version of the Kullback-Leiber divergence. So it's very nice, it's bounded by 0 and log 2, and it always exists. So imagine for the moment that we have at hand all possible functions in order to make the discrimination. I mean, we don't have a parametric model, we have much more than this, we have all possible functions. In this case, of course, the GAN problems can be written as follows, where I've just replaced the supremum over the parametric family by the supremum over all possible functions. And in that case, for fig theta, we can prove that this term is 2 times the Jensen channel divergence between the true measure that we want to simulate and mu theta, which is the measure of the generator, minus a constant. So it means that you can see the GAN problem as minimizing the Jensen channel divergence between mu star and mu theta. But of course, this is true only if you admit that you have at hand all the possible computational poles, say, or the possible functions of the universe. In practice, this is never the case. What you have is a parametric family, which approaches the family of all possible functions. And so, of course, you just have to replace the class of all possible functions by a parametric class. And of course, the game is then to understand how this, what you lose by weakening like that way, by passing from a parametric to the class of all possible functions. So that's for the traditional GANs. And for Wasserstein GANs, then the idea is to replace the Jensen channel criterion by the W1 criterion, which is the one Wasserstein distance between true probability measures mu and nu, which I recall here, it's the infimum over all possible coupling between mu and nu of the transport distance. And it turned out that there is a dual form of W1, which can be written in the supremum over a non-parametric class of function, the class of all Lip1 functions, Lipschitz functions with parameter 1, of the integral of f d nu minus the integral of f d nu. So that's really the connection between traditional GAN and Wasserstein GANs. And of course, in practice, W1 GANs, they have many interesting advantages. So immediately you can then define what we could call a theoretical W-GAN problem, which is obtained by minimizing the W1 metric between mu star and mu theta, exactly as we did before, except that now the supremum is taken over all Lip1 functions. Then of course you take the infimum and you get the GAN problem. In practice, you never have all the Lip1 functions at hand. What you have is a parametric class of functions. And of course, you just weaken the problem by replacing the Lip1 function by a parametric class, d alpha, parameterized, for example, by a neural network. So that's the W-GAN criterion. And of course, again, all the question is to see what we lose by passing from all the Lip1 function to the parametric class. And the empirical version of these is, of course, just obtained by replacing mu star by its empirical version. Okay, so there is a very convenient framework to study this business is to use the so-called IPM, integral probability metric DD-RON. So if D-RON is a class of function, then the IPM is just the supremum over the class of function of the difference between the integrals. And of course, we have immediately, with this notation, a unified framework. So for the theoretical W-GAN, then we have dLip1, which is the traditional Wasserstein metric. And of course, we have a set of optimal parameters theta star, which are the optimal parameters with respect to the Lip1 criterion, which is a good criterion. We have the concrete GAN problem, W-GAN problem, which is obtained by taking D-RON. So D-RON is the neural network. And of course, we have an associative set of optimal parameters theta bar. And of course, the empirical W-GAN, where we replace mu star by mu n. So the key is in understanding this D-RON, where D-RON is a neural network. So the properties of dLip1, they are very well known in the literature. There are books on dLip1, but the story is different for D-RON. And the question is, how do we pass, or what do we lose when using this neural network-based distance compared to dLip1? So that's the key to understand the way this generative models work. So let me provide you some interesting results toward this direction. I call this optimization properties. So first, I need some assumptions, but which are very weak in this context. So the distribution mu star is supposed to have a first order moment. The critic is sub-Gaussian. Of course, this is satisfied by all the traditional critic which are used in practice. And I will also assume that my network have bounded weight. So for the generator by a constant k, and for the discriminator by 1. So I just want the discriminator to be really one Lipschitz functions. So that's why I bound the weights in the appropriate norms by 1. And so the conclusion is that my discriminator is included in the class of Lip1 function. So the problem is well defined. In practice, this type of condition is implemented by using, for example, penalty on the risk. So the problem is well defined. And now, why using this particular group solved neural network? Well, in fact, we leverage on a very recent result, interesting result by Yann LeCun Gross from 2019. And these authors say that provided the space on which we are working is compact, which is not our case, but anyhow, then if you take a Lipschitz function on this space, then it can be approximated by a group solved neural network, which is still one Lipschitz. So it means that we can play on both sides. We can approximate very well Lip1 function by neural networks, which are also one Lipschitz, so much more stable with this respect. So that's very interesting, and it has important consequences for the analysis of W-GANs. We can prove that there exists a discriminator. So it means that there exists a depth and there exists a size of neural networks such that each neural network in this family of discriminator is one Lipschitz. The neural IPM is a metric on the set of probability measures you are working with. And the neural IPM metrises with convergence on the set of probability measures. So this means that we can find sufficiently involved architecture such that with this discriminator, then dlib1 and dd-run are topologically equivalent. That's essentially what it means. So it means that provided enough computational power, then you don't lose anything by passing from the parametric to the non-parametric case. Of course, please note that this is not a requirement that the space E is compact, so we have to work hard in order to delete this assumption here. So we can also have some results on the size of the neural net that do the job, but I skip this because it's too technical. So then, of course, we can go a little bit further by providing some results about the Lipschitz net of the different functions which are involved in the analysis of these Wasserstein GANs. And basically, we can have some interesting results on theta star, the set of optimal parameters, and theta bar, also the set of optimal parameters, but obtained with dd-run, so the neural net IPM. And for example, we can prove that these sets are non-empty. That means that there are indeed minima that we can find or try to find. Okay, so this is for the general properties on optimization. And of course, then the key is to introduce this error that we call the optimization error, which is the difference of what is obtained by using dlib1, I call the parameter mu theta bar, compared to the ideal that we will compute if we have at hand all the possibly one function, Lipschitz one functions. So this term, epsilon optim, is really what you lose by passing from the non-parametric class of function to the parametric class of functions. Of course, mu theta bar is not unique, so we take the supremum. So that's a non-negative term, and it is upper bounded by this quantity here that we call t, which really measures what you lose by passing from dlib1 to dd-run. And so, of course, this parameter is very interesting. It's decreasing when you get more computational power on the discriminative side. And on the other hand, it's increasing when you augment the size of the generator. So there is an interplay between these two terms. And still using the arguments that I presented you before, we can prove that if you give me an epsilon, then I can find size, particular discriminator, such that the optimization error is as small as epsilon as I want. So that's exactly in the same spirit as before. So the message here that for any generative model and any epsilon, you can find a discriminator so that the loss in performance is as small as you like. So we can have several results in this period, but again, the message is that this groups of neural networks are very good in order to approximate the dlib1 by dd-run. And finally, now some asymptotic properties. So in practice, as I said before, I never have the measure mu star, I have data. And so the real problem that we want to solve is the following one, when I have just replaced the expectation with respect to mu star by this empirical sum here. And so, of course, that's the infimum of dd-run, the IPM between mu n, the empirical measures, and mu theta. And so, as usual in machine learning, what we are interested in is to measure this difference. So dlib1 is the good criterion. Mu theta n is the parameter that we have computed empirically, and we want to compare with the optimum. So it's a non-negative term. And what we do is, since mu theta n is, of course, not necessarily unique, we immediately take a supremum over all the empirical parameters. And we introduce a first term, which is an estimation error. That's the difference between empirical and the best in the class with respect to dd-run. And of course, then we have the other error, which is the optimization error, which is what you lose, again, by passing from dlib1 to dd-run. So this is the sum of two errors. They are very different. The first error is due to the statistical fluctuation, and the second error is due to the, to the fact that you have a parametric model, you have a neural network. And so we can prove that the first error goes to zero more surely, so it means that you have statistical guarantee as you have more and more observations. And the key inequality is that the sum of these two types of errors is bounded by 2 times t, which that we have seen before, plus 2 times this term here, which is really interesting. That's the dd-run distance, the IPM distance between mu star and mu n. And we see the different effects here of the models. Of course, t is increasing when p is increasing, but on the other hand, the discriminator plays a much more ambivalent role in the sense that the first term is decreasing with d, whereas the second one is augmenting. So if we want to have further insight, then we have to understand the way dd-run, the IPM between mu star and mu n behaves. Again, this is very well known when d-run is lib1, but when it's a neural network, the story is different. So we have results toward this direction. For example, we prove that if mu star is sub-Gaussian, multivariate subgaussian, then this distance scales as 1 over square root of n, which is a parametric rate, but with a constant c, of course, which gets bigger and bigger when the depth and the size of the network get bigger. So putting all the results together, we can prove that if you provide me with an epsilon, then the sum of these two errors is bounded by 2 epsilon plus a constant depending on epsilon over square root of n. So we really have ideas about the rate of convergence of these two terms, which again are in competition. So that will be my last slide. Finally, we conclude that the error that we commit by fitting an empirical GAN, so that's DLIP1, between mu star, the target, and mu theta n, the parameter, which is computed by the GAN, is not larger than an estimation error, an optimization error, and this last term, which is an approximation error. So these 3 types of errors, and that's the message, have very different interpretation. The first error is due to the fluctuation in the observation. That's a statistical error. The second error is the loss in performance when we use a parametric model to approach the class of all LIP1 functions. And of course, the last error is the approximation error, because we use a model in order to approximate mu star. So, well, this is essentially what I wanted to say, Daniel, today. Thank you very much.
Thank you, Gérard, for the nice presentation. Do we have questions from the audience? Yes, Julia.
Okay, so thank you, Gérard. It was a really very interesting presentation and very deep results. So you said it was maybe too technical for this presentation, but would you have a very high-level conclusion about the size of the networks that you need to obtain these results?
Yeah, very good question. Julien, can you see my screen?
Yes.
Yes. So I just browsed, it's there. So at a very high level, what we show is that the depth of the neural net which is involved in the results is basically the same as the depth that we will get by using Relu neural network, but you need more bigger size, and so the complexity of this network is larger than the size of. Sorry, the complexity is larger than the complexity that you would use with the Relu neural networks, because these networks are more expressive. You ask, of course, much more by asking that the neural net has to be 1 Lipschitz. So yes, so these are more complex neural networks. So at a high level. Huh?
Okay, thanks.
You're welcome.
Okay, in the interest of time, thank you again for the nice presentation and the Q&A.
Thank you very much, Daniel.
Thank you. I'd like to move on to our next speaker, the last one in this session, Katharina Morik. She's a full professor at the Technical University of Dortmund and also director of the Dortmund Competence Center for Machine Learning. Katharina, please. I think you may still be muted.
Okay, so
yes.
There is a little knob and there is a little knob, so you have more ways to do it. So yes, I'm coming from the German Competence Center Rhein-Ruhr, which is located at the University of Dortmund, which you see in my background, and Fraunhofer Gesellschaft St. Augustin and the University of Bonn. And I will not present our research center except for just naming the focus areas that we work on: trustworthy AI, hybrid machine learning, how to use knowledge and bring it together with more data-driven models, resource-aware machine learning, where we consider energy, memory, runtime, and communication demands, and algorithms, especially for ultra-low power devices, quantization, model compression, because it's also for distributed Internet of Things applications, and submodular or core functions for data summaries, and then compiling for diverse hardware and also some quantum computing. So these are the areas, and I only go into the first one, Trustworthy AI, today. And there I also only give one research area which I'm personally very much involved in. So this is just pars pro toto. So there is ethical and governance aspects. Who are the stakeholders? That is handled by a professor of philosophy at our university in Dortmund. Fairness and bias, you know, that is very much of interest to all the machine learning people. Then regularizations, that is of my concern also, but it is, we have a lawyer, a professor of law at the University of Bonn who is involved. And then we come to what we do is certifying and documenting the overall process, that we want to have dataset enhancement and resource-aware optimization of the overall pipeline of machine learning and pre-processing and post-processing. And then inspecting and verifying methods that is done by explainable AI, where I have some PhD students working on that, and then guarantees based on tight bounds and robustness tests. And today I will talk about the latter 2 points. And I want to recommend the reading of Reflections on Artificial Intelligence for Humanity, which is the book edited by Bertrand Braunschweig and Malik Khalab as a result of our Global Forum on AI for Humanity. And the last days where we could all meet in person. Daniel, you remember quite well. So now let's come to certification and this stuff. And there are the proposals of model cards or fact sheets that were, the fact sheets were promoted by IBM, and the model cards were promoted by Google. And what they do is they give a guideline of what developers should write down by hand about their models. And what they do not do is they do not test whether all this, what the developers write down in words, actually is compliant with the theory of machine learning and with a particular model and with a particular implementation. And then all these, if you look into the questionnaires that they have proposed for the developers to fill in, if you look at that, this is completely not understandable for anybody who is not a machine learning expert. So I think it is also very important that it is comprehensible for non-experts, and therefore we have done something completely different. We have done something where you can certify the trained models, where you look for compliance with the theory, where you consider different hardware, where you make it comprehensible for non-experts, and where it is my particular concern because of sustainability to focus on energy consumption, to be resource aware. So this is what we did, and I show you how we've done it in a case study. And I think it is actually a task for the overall global community. So when I say human understandable, then my concern is not that I get a 2-hour course, but my concern is to take into account also the very restricted patience of people. Now, first step is, if there is a theory, why not using it? And here I have just shown you some things from probabilistic graphical models where I worked on. And then you see there are the algorithms, the complexity, the quality, and you see the junction tree, the loopy belief propagation, the tree-related max product message passing, the weighted integrals and sums by hashing, and our own stochastic discrete Crenshaw-Curtis quadrature. So, and there you see all the proven bounds. And why not using them? Why ignoring all the knowledge that we have? So we could use the theory to see what demands do our models from memory, communication, computing capacity, and energy. And therefore, I'm advocating triangular AI, where we have knowledge, data, architecture. And that's the ML2R approach. So the criteria, the care labels for the busy decider are intended to just with one glance give you all the information that you need if you are not an expert. So when I buy a washing machine, I do not want to have a lecture on engineering the water consumption of modern fuzzy logic controlled washing machines. No, I just want to see the A label in energy consumption. That's what I use for my buying decision. And so we thought, why not doing the same with machine learning and having the criteria given by machine learning theory, which we have represented in knowledge graphs in the background. And then we have the static, I don't know whether you can see my cursor. So we have the static description where we have expressivity, usability, reliability, runtime, memory usage, and some extra things like it can be run on a mobile phone, it gives uncertainty measures, it can be executed in a distributed session, and so on. So, and then we have an automatic process that maps a method to these labels from best to worst. And then we also have dynamic properties, which you see outside here, where we take a particular implementation on a particular execution environment and then measure energy, memory, and runtime. So let's go into an example that might illustrate the approach. So for a loss of likelihood, and as an optimizer, we have gradient descent. We compare the junction tree inference and the brute force inference and belief propagation. And then we have, these are the exact ones, and then we have the approximate ones, loopy belief propagation, variational inference, and so on. So these are the particular care labels which we have defined. And you see here what we have put in for junction tree and loopy belief propagation, on the one hand executed on a CPU, on the other hand executed on a GPU, and there we have the particular measurements, and on the other hand you see here the static things that have been checked. So you see here examples for those methods that have clear and tight bounds and therefore can be tested in this way. Now, if we go for deep neural networks, there we have a very different situation. So there we can only give care labels for trained models with their data sets. Yeah, the ones before, we don't need to, in addition, take the particular data sets, but here we need to have that. And then what we have is just, we have this model zoo and ImageNet, and then we have all these architectures, and we have a software package SOP, which we used for the number of flops and parameters counting, such that this might be an approximation of the energy consumption. Then we were measuring the average epoch time and number of epoch to reach the target accuracy stated by torch vision that did the counting on that. And here you see the results of our extensive experiments, where you then see that MobileNet v3 gets a label in accuracy as well as in runtime using less flops, and in memory. But the best energy is in AlexNet. So, and then you see here for robustness, we had all the tests on perturbations at various levels. And we used ImageNet C and ImageNet P benchmarks. Then we have the adversarial attacks on projected gradient descent, which is here called just noise. And then all the attacks that are in the program Clever Hands that you can find in the internet. So we used all this in order to test the robustness of these exact methods that we had there before. And then again, you see the different measurements, and therefore, this is what we get as a care label representation of the result of our many, many, many experiments. And so there you see that MobileNet v3 has a good rating in accuracy, runtime, and memory usage. It can be run on a mobile phone. On energy, it has a very bad rating. And you see here the different platforms. One is a CPU, and one is a GPU, and then here the same for ResNet, where you see it's all, well, not A, not D, and here AlexNet has a D in accuracy, but an A in energy. So what you see is model selection for the people that apply neural net is made easy, because now you can decide whether energy is so important in your application that you can cope with less accuracy, or whether accuracy is so important such that you can cope with having more energy consumption. Okay, how do we do that? Of course, I do not go into all the details, but this is the outline and architecture of our certification suite. So we have the theory with the themes, the things from literature, as I have showed you shortly with junction tree and loopy belief and stochastic discrete tensor, Curtis quadrature, and so on. And other expert knowledge, for instance, publications about AlexNet and so on. And so that is the expert knowledge. Then we have the particular implementation that is handed over to the certification suite. So you do not need to believe in what the developers write, but you test it. And then we are currently enhancing our set of benchmark data from the internet. And then we have our criteria branches, and then these call for particular tests that are executed then automatically. So you see this is all automatic, so that you just create the calls to test execution, and then comes automatically this rating by some rules that divide the span of results into A to D intervals. And yeah, so there are some rules as well that are used here. And then finally we get this as an output. Okay, so I think it is a community task. We have now done it for these two types of models, but there are many more. And it would be, it is an open approach to integrate more measuring, perturbation, robustness tools, and gather benchmark data sets on various hardware architectures. Of course, we would like to collaborate with other test suites. The connection to AutoML is quite straightforward. I think it can be seen easily. And we want to turn proofs into knowledge graphs, and these knowledge graphs are then automatically turned into experiments. So thank you for your attention.
Thank you, Katarina, for your nice presentation. Do we have questions? I would have one question. The quantitative evaluation that you do on the different metrics, that very much depends on the specific system you use, right? The specific hardware, etc. And so I'm wondering, how general are these results? How can they be deployed to other systems that may have different hardware architectures, and hence things like runtime, etc., might look completely different?
Yeah, that is the difference between the static and the dynamic evaluation that we do. So the static is general, and the dynamic one has to be measured. That's why I have shown this lower part of the care label, which is on a particular hardware measured. So what we do automatically is that we start the measurement using certain tools. But of course, you have to do the measurement on every particular architecture. That's why this is a dynamic part and cannot be taken from proofs, because the proofs are just the O notation, right? Mm-hmm. And then you want to have the milliseconds, and then you have to measure. And so that is why our care label is always twofold, has the dynamic and the static part. And what is automatic is that you call the measurement, and that you can then do it on your particular hardware architecture that you as a customer want to use.
Another question, I think your main focus is applicationers who want to use machine learning and who have certain requirements, and they can check which existing method is most suitable to their needs. But can this analysis also serve the development of new algorithms? So for example, if you say method 1 is very energy efficient but not very accurate, method 2 is very accurate but not energy efficient, can does this analysis allow you to somehow conceive hybrid techniques that ideally combine the best of both worlds?
No, I think that with the care labels, we move beyond the current description and trustworthy documentation of machine learning, where we want to use the theory to create experiments, large-scale experiments. That's what we do here. And on the other hand, of course, in our research, we develop new methods. And what I find helpful sometimes is we made a large structure for the knowledge graph. And in this large structure, you might find some blind spots where you say, oops, why did nobody look into this? Maybe we should do that. So that was actually why we had developed this first principle quadrature program, because we saw, oops, nobody walked into that direction. Huh? Then we do it. but that is, so this talk, I just said 15 minutes. So these 15 minutes are devoted to turning knowledge into experiments automatically, and trying to raise attention and looking for collaborators and exchange with other groups, how their knowledge could also be automatically turned into the static and the dynamic parts of K-level.
All right. I see there's no more questions. Thank you very much, everyone, for
Daniel?
One more question.
Can I still ask? Sorry.
One more, go. Yes. Yes, go ahead.
So thanks, Katarina. Just a sorry, just a question. So you're trying to extract this knowledge graph automatically from the publications. Is that already fully done? Because I think it's also super interesting to know, to automatically extract this algorithm was evaluated on this data set and compared to this other mentioning or reporting these numbers. I mean, are you already doing that?
No, that would be great. And of course, no. So currently the automatization is if you have the knowledge graph, then you do that. And the other point, when we were, I mean, it took us such a long time to do all the search processes and crawling and so on. And I think it would be also very important to really get the theory more clearly. Yeah, I could show you the part of the knowledge graph we did for probabilistic graphical models. And I think such things need to be done for all our areas. And automating that would be great, but currently it is knowledge driven.
Okay, so maybe we can talk offline. I still recall when in Dortmund I started to have a simple system.
Yeah, I know.
And we can maybe revisit it, I guess, by now, and maybe also talking to Henry Schitzer and whatever. There seems to be much more in NLP already that can enable that. That would be good.
Yeah, because we worked on programs with code a lot, and crawling programs with code, and then from there to the others. And yeah, it would be really fun to work on that together with you. I like it.
All right, that's a very nice concluding remark for this session. Thank you, Katharina. Thanks, everyone. We'll now take a break and for about 10 to 15 minutes, and we'll reconvene at 2:50 with the presentation of Yann, and also then following that, a panel discussion on the future of AI. So please stay tuned. back to the French-German Machine Learning Symposium. I'm happy to introduce the next speaker, and that is Yann LeCun from the Courant Institute in New York, and also Facebook AI Research. Yann, the floor is yours.
Thank you, Daniel. It's a pleasure to be here. Thank you for inviting me. So I'm going to talk about self-supervised learning and a particular framework, which I'm not going to have to go into the details of, to sort of explain a little bit how all the recent methods in self-supervised learning can be sort of described or explained, called energy-based models. So I think there are three main challenges for AI and machine learning going forward. One is to learn with fewer labels or fewer samples or fewer trials in the case of reinforcement learning. And that means sort of learning to represent the world or the data, learning dependencies between variables without actually training a machine for a particular task, but just, from unlabeled data. The second one is learning to reason or to plan. And this is kind of a thing that, there's a number of talks in this symposium on how you can make reasoning compatible with deep learning, essentially. That's, I think, the big question. And then the third one, learning to place complex action sequences and learning to represent them. I can't say anything about this. I have no idea how to do this, but I see this as a problem coming up as well. So one question we could ask ourselves is how is it that humans and animals can learn so quickly and so efficiently? And they don't use supervised or reinforcement learning, at least not much. That's not where most of learning is performed, or how most of learning is performed. Most of human and animal learning is performed in a form that we could call unsupervised, self-supervised, not clear how you call it, but that seems to be done by essentially observing the world and to some extent interacting with it. But a lot of it is just observing. And babies learn various concepts about the world, like intuitive physics, in the first few months of life, mostly by observation. And so the question is, what principles are used by biology for this kind of learning that we don't seem to be able to reproduce in machines yet, at least not to the same extent. So this is the motivation for this idea of self-supervised learning. And really, I think the ability to be able to learn about the world, like, a large number of basic concepts, intuitive physics, etc., is really the basis, ultimately, I think will be the basis for machines that can have common sense. I stole this, this is a screenshot from my friend Jitendra Malik, a friend and colleague at NYU, who gave a talk recently saying that common sense is not an accumulation of knowledge, actually, it's a collection of models. And so really what our machines should do at some point is learn models of the world, not just accumulate facts, if you want. Okay, so self-supervised learning. It's capturing the dependencies between variables or predicting everything from everything else. So let's say we have a segment of video. We show a piece of the video to the machine and we ask it to predict the remainder of the video that the machine hasn't seen, and then we reveal the rest and the machine can train itself to predict what's missing. So this is predicting the future, but you can imagine predicting pieces of information in the middle of the chunk of information, predicting the top of an image from the bottom, predicting the past from the present, things like this. Filling in the blanks, really, that's what self-supervised learning is about. So in self-supervised learning, there might be variables that you always observe, and we're going to call them X, and then variables you may be asked to predict. You may or may not observe them during training, but you'll be asked to predict them, and we call them Y. And sometimes there's no X, there's only Y, because we never know which part of the input we're going to be able to see. So there's two uses really for self-supervised learning. One is learning hierarchical representations of the world from unlabeled data, which could be which could precede a supervised or reinforcement phase. The second one is learning forward models of the world. So models that would allow a system to predict in advance how the world is going to evolve or what the consequences of its own actions would be, and that's required for planning. But the real technical question there is how to build systems that can represent uncertainty in the prediction, in the sense that there are many ways to produce the continuation of a video, and a lot of things can happen in a video that are all plausible, and you cannot have a system that makes only a single prediction. You have to have a system that can make a set of prediction. So that's where energy-based models come in. So energy-based model basically is the idea of replacing an explicit function, a deterministic function that takes an input x and produces a prediction y bar by an implicit function. And this implicit function f of xy, call it an energy, measures the incompatibility between x and y. So you feed it an x and a y, and it tells you how compatible those two variables are. So x can be the initial segment of a clip, a video clip. Y could be a continuation, and f of xy takes low value if y is a good continuation for x, and higher values if y is not a good continuation for x. Inference, becomes a little complicated to, if I give you an x and I ask the system what is the correct y, the system has to perform a optimization, basically find the y that is one of the minima. There could be multiple of the energy function f of xy. So let's say we want to capture the dependency between x and y here. X are both single dimension in this little example at the bottom, and we have data points that are those blue dots. Then the energy function that gives lower values to the blue dots and higher values to every other value of y for a given x is a good energy function for the purpose of this inference. Okay, and it doesn't matter what shape it takes, as long as it gives higher energy to bad things than to good things. Now you can often transform, if you're really want to deal with probabilities, you can often transform an energy-based model into a probabilistic model by basically using the Gibbs distribution, which gives you the maximum entropy distribution for a given level of energy. And take exponential minus the energy and normalize, and that gives you a probability distribution. It won't be a good estimate of probability distribution unless you train it with maximum likelihood, which you probably don't want to do, and I'll come to this in a minute. So there are several energy-based model architectures, and two main categories of architectures: the joint embedding architectures and the latent variable models. And there's variations of those. So joint embedding architectures basically are architectures where both x and y enter parameterized functions, let's say neural nets, and then you take the two outputs of those two functions and you compare them in some ways. Okay, doesn't matter. C of h prime or hx hy, I should say, is some function that measures the distance, for example, or dot product or whatever between those two vectors. And the reason this is a good approach is that there are multiple y's that might produce the same hy because of the invariance properties of the predictor that takes y as an input. And so all of those y's will have the same energy, which means now you have an implicit function that can give low energy to a whole set of y's, not just a single one, if you just were to predict y from x. So that is really kind of a good idea. Those kind of architectures have become extremely popular over the last year or so in image recognition. In fact, there is a form of this that goes back a very long time in the early 90s that I worked on at various times, called Siamese networks, where the two networks are actually forced to be identical and share the same weights. And there's a number of techniques, Perl, Moko, and SimClear, that have appeared over the last year or two that use this for learning image features. The second type of architecture is latent variable predictive or generative energy-based models. So those models produce directly a prediction for y, and so your energy function is basically the distance or discrepancy of some kind, divergence between you observe y and the prediction. But the way to parameterize the set of possible outputs is through a latent variable, and as you vary the latent variable over a set, then the output varies over a set, and this set represents the set of plausible predictions. If you have a distribution over the set of z's, then you have an implied distribution over the set of y bars. So that's another way of parameterizing the set of possible predictions. I used to be a huge fan of this kind of models, but I have to say that for images, they don't work as well as the previous one. I'll come to this. So how do you train an energy-based model? You have two methods, contrastive methods and regularized or architectural methods. So contrastive methods consist in basically having a bunch of data points, the blue dots here, pushing down on the energy of those guys, and then pushing up on the energy of other points outside, okay? And this works, but it's very expensive computationally, and it doesn't work very well in high dimension because you have so many dimensions in which you need to push up the energy that it tends to be really impractical. So those, were popular for a while, but they've been sort of, they're being kind of displaced, if you want, by regularized methods. So regularized methods have some technique by which, some regularizer, for example, by which the volume of space that can take low energy is limited or minimized. Okay, so when you push down on the energy of your data points, automatically the rest will go up because the volume of things that can take low energy is being kind of squeezed down, if you want. So here's an example of contrastive methods. You have a loss function here that takes the energy of a good guy, f of xy, and the energy of a bad guy that you pick somehow, f of x y hat, and maybe a margin, and you plug this into a hinge loss, and that kind of pushes up the energy of the bad guy above the energy of the good guy by that margin. Okay, that's an example. There are other loss functions you can use. I'll go to that in a second. For latent variable models, you need to have some regularizer here that limits the information capacity of the latent variable, because if the latent variable has, let's say, the same dimension as y, there's always going to be a z that's going to produce a prediction that's exactly equal to y for any y, including bad ones. And so what you get out of this is an energy function that's completely flat. That's not what you want. By limiting the information capacity of the latent variable, you actually limit the volume of space that can take low energy. And so you automatically kind of push up the energy of stuff you don't observe. The question is how you do that. So, oops, I'm not sure why this went back. Okay, I don't expect you to read all of this, but I'll post the slides later. But this is a list of a lot of classical methods that people have worked with over the years and classified as to whether they are contrastive or regularized / architectural. So things like masked autoencoders that are used in NLP, or denoising autoencoders, that's a form of contrastive method. GANs are contrastive methods. Siamese nets in the classical sense and metric learning are contrastive methods. But then in regularized architectural methods or regularized method, you have things like sparse coding or sparse autoencoders, variational autoencoders, BYOL, which is kind of an interesting method, and Barlow twins, which is a new method that I'll just talk about. So this is just, I'm not going to go into the details, but this is to show that there is a whole bunch of different type of objective functions that can be used for contrastive learning. And there's sort of a general form for them. And some of those go back a long time. Actually, people were using some of those objective functions for discriminative training or speech recognition system in the early 90s and for handwriting as well. The most popular one in recent years has been one that doesn't rely on just a pair of samples, a good one and a bad one, but a whole set of positive and negative samples or pairs of XY, and basically has some competition between them. So a good example of this is what's called InfoNCE, which is basically a softmax applied to a single positive sample, and then you divide by a denominator that has a bunch of negative samples. So this has the effect, minimizing this has the effect of kind of, minimizing the energy for the good guy and then pushing away, like maximizing basically the energy for the bad guys to the extent that they are too close relative to the good guy. So this type of the type of learning that has been really successful in NLP, in natural language processing, has been denoising autoencoders applied to text. You take a piece of text, you remove some of the words, and then you train some giant transformer architecture or even a convolutional net to recover the missing words. So it's an example of denoising autoencoder, which is an old idea going back to the 1980s, but sort of explained by Pascal Vincent in 2008. And this works astonishingly well. And you can interpret this in terms of energy-based models. I don't really have time to do this. And people, of course, immediately after that have tried to do similar things for images. So you take an image, you remove some parts of it, or you take a video, remove some frames, and then train what amounts to an autoencoder essentially to fill in the blanks. And then you look at the features and you use the features as input to a subsequent downstream supervised task. And this doesn't work very well. It's been very disappointing. And the reason is probably that it's easy to, the reason why it works in NLP is because it's easy to represent uncertainty in NLP. because words are a discrete set, not so easy to represent uncertainty in a continuous high-dimensional space like images or image patches. So here is what's really how contrastive joint embedding works in the contrastive setting. So you have your energy function, which measures the distance between two halves. Generally, those two halves have shared weights. You show it a positive pair, and you make the distance as small as possible. You show it a pair. So those two, this positive pair corresponds to two images that are basically distortions of each other. And so they're semantically similar. And so you ask the system to produce representations that are similar for those two images. And then you show two images that are different. And you try to make that distance high, essentially, using some loss function. You know, this, so what you do next is you chop off the last few layers of your network, and you use the representation as input to a linear classifier. You train this linear classifier with label samples and measure the performance. So that amounts to basically a multinomial logistic regression. And this works pretty well, but it's very expensive. Those things use generally this InfoNC criterion. So this is a list of techniques that have appeared in the last year or two that use this technique. It works really well for speech recognition. You can reduce the amount of training data you need for a good speech recognition system for about 100 hours to about 10 minutes with pretty much the same accuracy, which is pretty amazing. This is work from some of my colleagues at Facebook. But here is the cool thing. The coolest thing now that has appeared over the last few months, basically, or year, is non-contrastive energy-based model training, particularly for joint embedding methods. So we talked about contrastive, that's the stuff on the left. And then there are distillation methods. So distillation methods are methods where you basically force the two encoders to be more or less identical. You stick a predictor on top of one of the branches, and you don't backpropagate the gradient in the right branch. You can, this red cross here says don't propagate the gradient. The two methods that are most interesting for this are BYOL and SimSiam. So SimSiam from Kaming He at Facebook, BYOL from DeepMind. There's quantization methods. They are basically the best working method at the moment. Suave in particular, that came out of Facebook AI research in Paris, together with INRIA. And the idea is that you have a branch that you don't train, but the weights are shared with the left branch. And you perform a clustering on top of it, k-means or something like that. And you use the vector of assignment, if you want, of the training samples to the clusters as basically a target to train the left branch of the system. This works astonishingly well. This is probably the top dog at the moment, although the difference with other methods is very small, but this works really well, and it can be trained with very large distortions, which is an advantage. And then the last category here, which I'm going to mention in a second, is something that attempts to maximize the information content in the code, which is a way to prevent collapse, essentially. So all of those methods, the complexity is to prevent collapse. If you train two neural net to produce the same output for similar images, and you don't do anything else, it will collapse. It will basically ignore the input and produce a constant output. So all of those methods, contrastive methods, distillation, quantization, and information maximization, are ways to prevent the system from collapsing. So basically a way to prevent the system from producing a flat energy surface and to only give you low energy for stuff you train it on. This is the type of network that is used in things like BYOL and SimSiam and MoCo, where you actually slow down the weights of one of the branches, and for some mysterious reason, it actually makes the thing not collapse. The quantization method, Suave in particular, and Deep Cluster before that. This is the team from INRIA and Facebook AI research in Paris. Works really well. The Suave is one that is kind of a symmetrized version of this, which I don't have to go. I don't have time to go into the details of that. But this system can be has been used for experiments, large-scale experiments, where you pre-train a fairly large convolutional net on 1 billion random images from Instagram. And then you fine-tune the network on ImageNet, and you can get 84% correct. And this is kind of the first instance where a self-supervised system, basically works better than a purely supervised system. Of course, it uses more data, but it's unlabeled data, which essentially is free. And it works really well also when you only train on 1% of the labeled images of ImageNet, you get 60% or so. So this is Barlow twins. This is very new. The paper actually has been on archive for a while, but it's an ICML paper. We've learned that a couple of days ago. And the idea there is you have two identical halves, so the two networks share the same weights. This is a standard ResNet 50. The dimension of the representation is 2048. You run this through a few layers of like a multi-layer net called a projector. And the output of it is something like 8,000 or 16,000 dimensions. And what you do here is that you have a loss function that tries to make the cross-correlation matrix, the normalized cross-correlation matrix between the vectors coming from the left half and the vectors from the right half as close to the identity as possible. So basically you're saying variable number I on the left side should be very highly correlated to variable number I on the right side, as you know, correlation should be 1, but variable I should not be correlated with variable J on the right side. You want to make the normalized cross correlation 0. So that's the loss function here at the bottom. And so you don't need any contrastive samples, and you get really, you know, very good results here. So it's better than SWAV without the multi-QAP, but it's not as good as SWAV with multi-QAP. It's about, you know, a couple of % below. It's about the same as BYOL within kind of, you know, decent margin. And it's a very simple algorithm. It works really well also on transfer tasks and sort of, you know, the low data regime. So I'm really excited about this kind of technique, and it's a little bit new in the context of self-supervised learning. Okay, I'm going to skip this because I'm out of time. This was about learning forward model and go to conclusions. So I think self-supervised learning is really the future of representation learning. I think it's the future of machine learning, actually. You know, contrastive reconstruction-based SSL works really well in NLP, but not so well in images. In vision, contrastive prediction-based SSL works well in speech, but not so much in vision, unfortunately. Reconstruction prediction doesn't work well for images. Joint embedding methods work better for images, so that's probably where things would be going. Contrastive joint embedding is too expensive, so the most promising methods are non-contrastive, things like BYOL SimSiam, a clustering method like SWAV, or information maximization methods like Barlow twins. I think we can use those techniques to eventually kind of train systems to learn world models that can predict under uncertainty and use them for control. Thank you.
Thank you, Yann, for the nice presentation. In terms of timing, we're already part of the panel discussion now. So I suggest we just combine the two and we start with questions to Yann, and then we can broaden kind of the discussion, if it's okay with everyone, towards kind of talking about the future of machine learning in general. But let's stick with self-supervised learning for now. Let me maybe start with one question, if I may. You motivated self-supervised learning with humans that also do a lot of self-supervised learning. If I look at my kids, they do that indeed. But you know, maybe this is overestimating my responsibility as a parent. I do believe some supervision seems to be necessary for children and possibly for machines as well. And I think one aspect is, if you do purely self-supervised learning, then you may be able to reproduce patterns in images, patterns in language. But the question is, how much do you actually understand about the world observed in these patterns? And I think this is a little bit harder to measure, though, right? I mean, you can easily measure how well images can be resynthesized, missing parts in language, in images, but how can you measure how much a machine understands about, say, the language it reads?
Well, so I think as humans, because we are humans and we rely a lot on language, it's very important to our species, we overestimate the importance of language for intelligence. And so we think that, and as a consequence, we also overestimate the importance of social interaction and sort of supervised direct teaching, if you want, for intelligence. There's no question it's very useful for humans, but there's a lot of you know, animal species that, you know, learn a lot of stuff, and they're pretty smart, and they basically don't interact with any of their kin for, you know, during their youth. You know, octopus is a good example, but you know, even a baby cat, right? Baby cat is pretty smart, has a lot of intuitive physics knowledge, actually an amazing level of intuitive physics knowledge that they learn in the first few months of life. They're not being taught much. Most of the stuff they learn by themselves. So, I'd be happy if the only kind of intelligence, we can reproduce within my, before my brain turns into mush, is, the level of intelligence of a house cat. We're not at that level yet. And then, after that will come, okay, how do we deal with language and, explainability and, things like that. But I think it's, we have a first mountain to climb, and we know there are other mountains behind them, but, I'm just interested in the first mountain now.
Okay, yes. So I would suggest let's open the floor for the panel discussion. There's no specific panelists, but the aim is to discuss a bit freely. Everyone can contribute a little bit. Maybe if people have questions to Yann immediately, please, if you are happy with it, switch on your cameras so we can see everyone. Klaus, you're waving your hand.
Okay, yes. I still had a question to Yann, because I'm very intrigued by these energy-based methods, and the way you described it was very simple. You push the solution that you have down and make everything go up. That was the short version of it. I mean, since I'm not a specialist in that, is there anything known about how to do this optimally and how to do this robustly? Because I can think of many ways how this can go wrong.
Oh yeah, me too. I mean, I've seen many ways in which it can go wrong.
Yeah.
Okay, so here's a way it can go wrong. If you use contrastive methods and you are in a high-dimensional space, you push down on the energy of the good guy, you push up on the energy of some bad guys that you pick in some way, and the question is, how smart are you at picking them? So here is a way to attempt to be smart about it, is to say, I'm going to compute the exponential of the energy of that my model gives to a particular point in the space, okay? And I'm going to pick that point with a probability proportional to e to the minus that energy. So that low energy things will have a higher probability of being picked. And I'm going to push those guys up, okay? In probabilistic modeling, this is called Monte Carlo methods. This is exactly what Monte Carlo methods do when you do maximum likelihood in probabilistic modeling. You have an intractable log likelihood function because of the log of the partition function, and you want to compute the gradient of this, and it ends up being an integral that ends up being some average of gradient. And the way you do this is you sample from your model distribution to approximate this integral by a finite sum, and that's called Monte Carlo, right? So that goes wrong because in high-dimensional spaces, there are so many places you need to push up on if your model is flexible that basically it's ridiculously expensive. So that's one way it can go wrong. Now the second, the other way is how can you design a loss function of the type that I talked about in an architecture that either maximizes the information of the code or minimizes the information of the latent variable, which is basically what you need to add to the code to predict the variable to be predicted. So you can either maximize the information content of the code or minimize the information content of the latent variable if you have a latent variable. And the question is how you do that. A good example is sparse coding, right? Sparse coding, you minimize the capacity of the code by making it sparse. And the problem with this is that it can still lead to collapse because if you need to normalize your decoder, because otherwise your latent variable can shrink to 0 and your system will not learn anything. And so, there is no recipe, complete ironclad sort of theoretical thing that says, here is what you should do, other than something I wrote in a tutorial in energy-based model in 2006, which is you need to have a loss function that guarantees that the energy of stuff outside the stuff you train on is higher than the stuff you don't train on. But
yeah, so essentially you need to regularize properly.
Well, so this information capacity regularization of latent variable is a form of regularization. Yeah, you regularize the shape of the energy so that the volume of stuff that can take low energy is minimized. But very little is understood about this theoretically, right? So probabilistic models are very, very narrow special case of this, right? But there's a whole world outside of probabilistic models, and this is what becomes interesting.
I think a challenge that I find interesting in the context of self-supervised learning as well is really trying to understand the world behind the observations, right? Be it language, be it images. So in computer vision, for example, we've been very focused on analyzing images and videos, maybe, checking how well can we fill in holes, etc. How well can we classify, how well can we reconstruct geometry from multiple images. But I think what's still missing, if I look at humans, they seem to also infer, for example, the physics in the world. Let's say you play tennis, right? You see a tennis ball playing, you can somehow predict the whole trajectory of the tennis ball all the way to where it impacts, right? And the time of impact, all of this. And my impression is, at least in computer vision, we're still very far from that kind of more holistic analysis of the world that is being observed with the camera. And we often stick very close to the observations more than actually the underlying phenomena somehow.
I mean, there are quite a few attempts at this people in robotics that try to kind of heavily use machine learning in the context of robotics. Are actually trying to kind of learn intuitive physics from video, essentially, or the effect of actions, for example, from video. I mean, I'm thinking of the work of, Chelsea Finn, Sergey Levin, Peter Abil, etc., the Berkeley crowd, which is now the Stanford Berkeley crowd. There's a lot of interesting work in this area. They're not the only ones working on this, of course. I mean, there's people in Europe, people at Facebook and other places who are working on this kind of stuff. But yeah, I mean, if you have a forward model, which is something I didn't have time to talk about, that takes as input the current estimate of the state of the world, the action you take, and predicts the next state of the world, then you can essentially plan. You can use that for planning. But that begs the question of causal inference. Like, how do you identify the causal graph of things in the world? This is something that Bernhard Schölkopf should tell us about.
I think you'll be speaking tomorrow, Bernhard. You want to add a little bit on causality and causal inference?
I mean, there were, first of all, I think this was a great talk, great intuition about all these different things. Now, there were multiple places, of course, in the talk where I would have thought, well, okay, this would be a place for causal inference to be mentioned. Or when I think about this problem, I think of it in terms of causality. And but I respect that you think of it differently, of course. And also, I think, I think the space of all possible problems for which you can find a sensible acyclic causal graph is relatively small. So I think the real world is more complex, and I don't want to claim that all of it can be explained by causality. But I think, I mean, for instance, at the beginning of your talk, you had this overview of sort of what are the open problems of machine learning. So I think one of them was learning with fewer labeled samples. Second one was learning with reason, and then you had learning to plan action sequences. So I would think causality has something to say about all these three, but I think it's still open what will be the final resolution.
I agree.
Would anyone want to share a little bit their view on?
I would be happy to react to what you say, Daniel, about the underlying phenomena, like the ball in free fall mode, which is something that we are very that is very easy to model, actually. And when we apply this model in robotics, I don't really agree with you, Yann, if I can. In robotics, the last very nice success that were obtained, they were really obtained with models, and they were strongly based on empirical models that are described by the engineers, like models of physics, because actually we are very good at modeling physics with our algorithm, and not so good at learning them, in particular generalizing them to data that have not been observed exactly, and getting this some database models to fit to the level of accuracy that we need in robotics is something that we are not yet able to do. And then I'm a little bit surprised that we are not able to adapt the machine learning methods to account for this knowledge. So basically, phenomenological models, they are differentiable, So they would typically enter in a differentiable programming framework. They could be put as a kind of extra neural network layer and work with backward propagation. That would work without any problem. And I'm surprised that we are not able to do that. And in robotics, to me, it's one of the main limitations that is preventing machine learning to make big success that we see in vision. Because in robotics, we have strong models, and ML is not able to adapt to them. So I don't know if you think I'm overreacting to what you say. Yeah.
I also think that maybe humans don't necessarily take models, right? So if I see this tennis ball example, if I can catch the ball and predict its trajectory very precisely, I don't think in my brain I'm integrating the Newtonian equations of motion, right? I'm not doing anything like that, but somehow I can still extrapolate fairly sophisticated movements without, having a brain that can compute the Newtonian equations and integrate.
Well, I mean, it's plausible you can't, but it's plausible that you may, who knows? We don't know how our brain works, right?
Good point.
I think there's a whole spectrum of models, right, of how you can approach the problem. You can build a model completely by hand, which of course you can, if you're talking about a robot arm that is completely over actuated with PID controllers and enormously powerful motors. Most robotic arms are actually that way. Then you can model the dynamics, and you can write down the equations, no problem. There's maybe a few parameters you need to do system identification for, but that's easy, right? And then at the other extreme, there is a model of dynamics that's completely learned from scratch, or maybe with a little bit of prior knowledge about what the nature of the model is. And people are working on those kind of stuff, right? Models where you put a little bit of physical constraints in, not a huge amount, just a little bit of it, but just so that it drives the system. Think of it as the sort of control equivalent of convolutional nets, right? Convolutional nets have a little bit of knowledge about the nature of the signal they look at, but not too much, and that would be a bit of the same. Now, the thing is, it's true that simulation works really well when you have an over-actuated arm that doesn't touch anything. As soon as your arm is touching an object, particularly if it's a non-rigid object, and there is friction, or you're trying to grasp something, your simulators basically don't work. As soon as you have an actuator that is an arm which is not over-actuated and has resilience to it, or flexure and stuff like that, which is what our arms are essentially. Then your models are not that accurate anymore, and there's a lot of nonlinear effects and a lot of dynamical effects that are very, very difficult to capture in a set of equations. So you need a phenomenological model to pick up the slack, even if you have a bit of prior knowledge in it. And that's where you need to learn the models. Now, those things are still fairly deterministic. The real difficulty is to learn models that are inherently non-deterministic, right? I put a pen vertically on my hand, and if I let my finger go, the pen will fall, but every time I do the experiment, it falls in a different direction. You can't model that dynamic other than by having a higher level representation that says the pen is down as opposed to up, but you can't tell in which direction. I mean, there's a lot more to modeling the world than writing down physical equations, I think.
How do others feel about what are the main challenges in machine learning? Bernhard mentioned causality, causal inference. Thomas, how do you feel? What do you think?
Yeah, I think the key problem when you move away from supervised learning, where you get all these class labels as abstract knowledge, to unsupervised learning, is that the abstract combination is missing. As all this contrastive learning and so on that we have, or mask filling, it works well in making the instance-based predictions, but it cannot establish the links between the abstract entities. And yeah, I think that is a key challenge on how to establish that without actually explicitly giving the abstract labels to it.
Mm-hmm. But I do agree that self-supervised learning has a fascination, and this is something I've always found fascinating when I look at my kids. Right, from very early age, they constantly watch everything. Right, and then I checked. What do we do in computer vision? We develop machines that can classify images, and they basically say, is there an airplane in the image? Yes or no. Right, so they're trained to classify. And then I looked at my kids and I was thinking, what are they doing? They're not really classifying at any given time. I think they're mostly trying to predict the future, right? And checking how well is their prediction consistent with what happens next, right? And I think you learn most when things happen that you don't expect. Like if you're in a restaurant, right, and someone drops a glass, right, everyone looks. Why? Because something happens that was not predicted somehow. So I think humans consistently have predictions about the future and align them with what actually happens. And that's a form of self-supervised learning as well, right?
Daniel, I tried earlier to show a slide. I don't know. Can I try again? Can I share my screen?
You should be able to do that.
Okay, because I tried and I think it was up for.
We saw it, yeah. We saw
okay, because that's what I really mean it. I think today that's what we are doing. We are putting in vision, at least, we are putting symbolic labels. Symbolic labels on objects. We don't understand anything at all in vision. So, a bunch of people put things in a bag they call a tree, but they don't, the machine learning machine doesn't know what a tree is. It knows how to put A, B, or C, or 0, 1, and 2. And I think that's a real, I don't in other subfields of machine learning or AI or whatever, but in vision, I think that's a real problem. We don't recognize objects. And to me, and I have no idea how to do that. And in vision, we have another real problem is that we don't know what the right granularity for the representation is. So should this guy paint his dog and his cat, or should he also paint the cat's whiskers, right? And it's due in part to the fact that, at least for language, I think there is kind of a natural vocabulary for talking about stuff that we don't have in vision. So even though we haven't seen a lot of progress in vision, I think we have very far to go.
Yeah, I think in many ways vision seems to be more difficult than language or language processing. First of all, language tends to be inherently one-dimensional, which makes some algorithms significantly easier, dynamic programming type of techniques that are much harder to get worked, that do not generalize to higher dimensions, to 2 or 3 dimensions that we have in images. But also, I think one difference is in language, language has a purpose. You have all this communication theory of Shannon that the language conveys a specific message, whereas with images, you take a picture, there's not necessarily any message, it's just an observation. So there's no, receiver, no. So in that sense, I think the challenge is different.
If I can comment, I mean, I think language is one of the bottlenecks. No? I mean, we can, most of the time, only can do one thing. Now we can go or we cannot go, or we can do A or B, but not A and B in general, at least, or with some restrictions. And the same is with language. Now we can think many things, but we can only say one thing at a time. So, I mean, some people call it these central bottlenecks in the brain, and maybe it's also a means to focus on certain issues, at least for a certain amount of time. And then there are probably a lot of other reasons why language was developed. And I would agree with maybe Yann, or of course I agree with myself mostly, that maybe logic and logical reasoning maybe came out of argumentation, but that's definitely quite late and quite sophisticated. But language might have other purposes as well. It's sort of a focus of attention in your brain. And one type of bottleneck, which is you cannot make it parallel.
Bernhard, I think you raised your hand.
So there's another. By the way, this Gary Larson cartoon. I think there's another way to discuss that even without talking about language, and that's if we connect back to the earlier topic of world models. So I think in the end, if we just treat the world as a big classification problem, then we end up in this Gary Larson situation. But if we not only recognize these entities in the world, but embed them in some kind of world model, such as a causal graph that tells us what happens to them if certain interventions happen, etc., then it gets interesting, and then you can ground these entities in these objects in the world or in a model of the world, and then maybe language can then be a next step when you start communicating about such models with other agents.
Joey, I think you also raised your hand.
Yes, I mean, I was going a slightly different conversation, one a slightly different discussion in direct direction, but it's interesting for me to contrast what was being discussed about performing tasks that we know how to perform as humans, like, you know, this understanding of the world, with what we do more in applications like health, but other scientific applications where the things we're trying to do are things that we don't know how to do, and even specialists don't know how to do, like combining genomics data and imaging, bioimaging, and all those sort of things to predict what is the best treatment for you. And I'm wondering if in this context, it's actually nice that we have ways of doing that without mimicking too much the human brain, because the human brain apparently isn't capable of doing this task.
Yeah, on that note, I actually have a question for Klaus related to what you just said, Chloe. So Klaus, I know you've been working on trying to use machine learning to predict properties of materials and chemical reactions and molecules. So this is an example where, although we do have a sort of reductionist model of everything, we can't actually compute with it to the extent that we can predict, for example, the function or even the shape of a protein or the properties of a crystal or solid. But an increasingly large number of people now are using deep learning to basically learn phenomenological models of those and attempt to predict properties of materials that we would not otherwise be able to predict.
Yeah. So it's becoming a very active field. And you're absolutely right. Data's scarce there. You just you need serious supercomputing in order to get a small data set. Just if you would like to get quantum chemical properties of materials, every data point costs you 3 to 4 months of computing time, and gives you something like a terabyte of result per data point. So it's a bit of a very upside down situation. So I think in this case, and that tying into the discussion what was said before, I think one of the interesting points is to use these machine learning models that you have as purely predictive or phenomenological models to see how things, to get insights about mechanisms that could be there, and to go back to physics. And this has been having some success, and we made some progress along these lines. And one of the questions there is perhaps, if you would transfer this to the computer vision world, is to see what, belongs together, in a way semantically. Of course, in physics, things don't belong together semantically, but rather physically. So we talk about collective variables. So collective variables are usually found by physicists that think about this for 30 years and afterwards get the Nobel Prize. So collective variables are phonons or plasmons or everything. So in a way, an understanding of a certain mechanism actually comes with discovering them. And if we could shortcut these 30 years a bit, it would be nice. But we're not yet there. But it's a very important open question.
So to me, I find this a very fascinating question, that the one you also hinted at is this inferring the physics of the world that we live in. And, you know, it's not just the tennis ball, but, you know, with everything that you interact with, even from visual observations, you can see the elasticity of objects, for example, right? I can, you know, if I see a bouncing ball, I can see, is it a hard ball? Is it a softer ball? So I can infer all of these properties, in fact, in fractions of a second from a few observations. And I think this is very important to try to get to that level of understanding the world. We had a paper last year, CVPR, where we showed that indeed we can take an elastic finite element simulation of an object and fit it to video observations. And one of the things we observed is that fitting this elastic finite element simulation allows you to infer the physical parameters like elasticity and Young's modulus directly from the sensory observations. But in addition, we saw that this allows you to actually simulate what happens next. And you need very sparse observations only of a bouncing ball, or like a bouncing, in this case, teddy bear, to predict the evolution of things over time. And my feeling is that humans do that. They infer many physics aspects of the world around them in order to simulate what happens next, in order to enable more long-term predictions of what happens. And I think this is something that we've not really looked that much into in computer vision. Can we devise methods to predict the future observations? And I think that's what humans do a lot. You know, obviously, evolutionarily, the better you can predict what the tiger in front of you does, the longer you live, right? So I think predicting the future is something that is super vital to humans. And it is a form of self-supervised learning, because we get a constant supervision signal with every new sensory measurement coming in. We can align how well is our prediction of what happens.
I think Katarina wants to say something.
Oh, Katarina.
Yeah, it is funny that we now come back to the old discussion of cognition on the one hand and modeling on the other hand, because there has been a lot of investigations in the early days of artificial intelligence and machine learning, and that were directed towards cognitive explanations. And the other thing really is that I think we should really discuss the model type that we are investigating. And if I understand you correctly, Daniel, you are talking about actions that can be performed. So in early days, I had a robotics project where I wanted to test my hypothesis that language is only understood with respect to action. So a cup can be only understood if you drink from it. All the descriptions that it needs to have this shape and be concave and so on is not at all important. You test it by taking it, trying to drink from it. If yes, it's a cup. If no, it's not. And that is a completely different type of a model than the true description. And therefore, if you combine the model with the world in perception and action, then you are certain that you can handle language appropriately, I think. And that is actually what children always do. They do not learn the formula of the ball. They know, if I can grasp it and I can throw it, then it's a ball, and that is it. And so I think we are back to something that was stimulating a lot of research in early days of AI. And I think we can now focus the same topics again at a better level, at an enhanced level.
Yes, now we have 3 people raise their hand, Jean, then Charles, and then Christian.
Okay, I just want to say that for for issues of modeling and predicting the future and how you can use that for locomotion, for example, or for walking. I think Nicolas Mansart has probably interesting things to say about that.
Me? Let's give him some time to think about it. Charles, I think you wanted to say something.
Yeah, I just wanted to add that, in fact, we are discussing about mostly concept and method. And I think the machine learning community is clearly advancing toward a very great methods and models. But I think we should also think about new technique to evaluate and compare the method we propose, because in terms of the situation, self-supervised, semi-supervised, and when you try to combine images, text, etc., I think we are quite weak for the moment in terms of a way to evaluate. Most of the time, it's again a balance in the supervised context or on the same data sets. So I think there is also some work to do on this sides to, of course, be very good at the method, but also on the comparisons.
Christian.
Yeah, I just want to remind all of us there is a lot of work in computational cognitive science, right? It's not like they are not working on that. So I think Josh is doing an amazing work also in trying to understand from a still image, what is your intention and where are you, will you grab the ball or not? There's also going deeper work because Gigerenzer and other people in other domains, they typically claim that we do everything by heuristics, and it turns out it's not a heuristic, it's optimal. I mean, you can come up with a mathematical formulation for catching balls, and it's not a heuristic, it's optimal how we solve it. So I think one of the, for me, that means for the future of machine learning, we have to deal a bit more with cognitive scientists again, just teaming up. I mean, we can learn a lot also how to set up experiments. But that also means, and it reminded me of how Yann started to motivate at some part, at least his talk, by saying it's not only world knowledge, but we need really bunch of world models, or a world model is a bunch of models. So I think there's the engineering obstacle that we should try to get over, right? I mean, how to really engineer complex AI systems. So it's something independent of what we discuss here, where symbols pop up and how do we get that? But just from an engineering discipline, how can we come up with complex AI systems where you have different algorithms and so on? So that would also help to not always ask where do the symbols come from, but just use them as a programming language tool in a sense. That seems to be, for me, quite important stuff. But really talk more to Josh, and there are other fascinating computational cognitive scientists, quite a lot to learn from.
Nicolas.
Thank you. So as maybe some of you know, I'm working with locomotion robotics. And in general, I would say in generating movements in robotics, and actually we are not very good at extracting symbols or reasoning. So like cutting the movement in slice of symbols, which is very appealing, right? When you are doing locomotion, you would say that you would have a slice of movement between two contacts, and that maybe making one contact would be one symbol. And then locomotion would just be playing with one symbol of right foot contact with one symbol of left foot contact. That's very appealing. And actually, it's not working well. What I mean is that this very straightforward way of working is not leading to much better results than other methods that are not trying to abstract these proto symbols of movements. And actually, if we are trying to work on a full trajectory where contact is abstracted as something smooth in time, so something that maybe you are making a contact very strong or very smooth, or maybe no contact at all. So that would be a layers of trajectories that are differentiable in time. None of that is making a big difference in terms of what the way that our motion solver are able to apprehend the movement. So it runs that maybe that's a reaction to what Jean said about extracting objects, recognizing objects in the world. like recognizing piece of actions in a movement so that we can plan this movement. And actually, it's not working that way. The movement is something continuous, and you cannot slice it like a language of movements. It's very more like fundamentally working as a single object that you have to manipulate. So I don't know if it's a reaction to what Christian say. I would say it's a kind of going on the other direction to what you say, Christian. Not working with symbols at all. And that's only an example from robotics, right? So maybe it's not applicable to something else.
I think what I wanted to point out is that, so let's say you're building your robot. Now you would like to come up with a unit test, right? And now you have a complex AI system. So for me, a unit test is something like you would write down, if I predict, if I see on this image now in this frame one car, and I skip one frame and I see again a frame, I would like to see everywhere a car, because it's such a short time period. Right now, it's logically not true. So you want to have a weighted constraint there. Like what Yann was talking about, we should talk much more about constraints. Now, how do I formulate constraint as a programmer? Well, via symbols. So I wanted to, whether you believe we provide symbols within the cognitive part, so to say, or you just see it as an engineering problem. For now, it's good to have a symbol because we want to put our constraints there. That's all I wanted to say, right? So I think we agree in a sense on a certain level.
There was something also that I found intriguing in Yann's presentation, and that is he talked about learning-based approaches, self-supervised learning, but then also these energy-based approaches. And that got me thinking that in computer vision, at least, you know, everything we nowadays do with deep networks, image segmentation, classification, optical flow, etc. You know, we used to do this by means of inverse problems and energy-based approaches where you set up a loss function. I think you all still remember that time, right? When we used to set up loss functions and then we minimized them. And I think one rather fascinating challenge that I know Michael Müller has been working on is how to combine these two approaches, how to bring them together. The more, you know, the learning-based approaches that tend to have lots of examples and training data, and then on the other hand, these more traditional, you know, inverse problems approaches that often try to find solutions just on first principles basis.
So if I can answer that, I think you make an interesting point, which is that there was a whole period in computer vision or image processing where, you know, the trendy thing was to come up with some energy function that you know would you would design the energy function, like, you know, the famous Given and Given paper and the snakes and all the, you know, active contours and all that stuff, right? And all kinds of other techniques. You know, the techniques that Jean has developed for 3D reconstruction, right? PNVS. It's all based, you know, it's all based on you come up with an energy function, and then using some gradient-based techniques or not, you try to find a minimum of that energy, and that's the solution. So that's how you solve so-called inverse problems, right? Now, the problem I'm interested in is how you learn that energy function, okay? So basically, you're given a set of samples that are presumably the minima of some energy function that you don't know, and you want to learn that energy function. What energy function are you observing? You know, your data points are the result of minimizing some energy function, and what you need to do is infer the nature of that energy function. And you have to do this with a loss function. So the loss function is what you minimize during training, and what it does is that it shapes the energy function. The energy function is what you minimize during inference. Okay, those are two different things in my terminology, right? It's not everybody's terminology. So I think to some extent it sort of merges the two, like, you know, the old sort of traditional approach of computer vision of minimizing, you know, doing inference by minimizing an energy function, which is also what everybody in, you know, graphical models and factor graphs and all that stuff, that's what people do, right? You minimize an energy function to do inference, essentially. Sometimes it's a free energy, sometimes it's not, but that's what you do. So that there's that, and then there's the problem of learning the energy function. That's what I'm interested in.
Yeah. And now we have Nicolas Ayash and Michael Müller.
Yeah, just to say that also I enjoy very much your presentation, Yann, and I look forward to read latest, to reading the latest papers. And in our field, in medical imaging, it's clear that we have a lot of prior knowledge. And so it's always tempting to try to find what are the constraints that we can introduce when we do some machine learning. And the gain usually is it's a way to limit the number of examples we have to provide. And also, and this is really very important in our field, it's often a way to improve the robustness of the results. So this is just what I wanted to say. I tried to show some examples this morning on that. And there is always this these ideas of trying to introduce some constraints from the anatomy and the physiology.
Michael.
Yes, so maybe commenting a little bit on this combination of model and learning-based methods. Well, I still have a talk tomorrow to comment on this in detail, but maybe sticking to our discussion here, one reason why incorporating prior knowledge also in what you meant with like finite element simulations, physical models or so, would be the question, do we really expose our machine learning methods to a lot of data yet? Because really thinking about what an infant has seen before it starts realizing this is the trajectory of a tennis ball is of course also moving in 3D space, experiencing the 3D world, which is quite different from our networks that we trained from scratch for maybe a week on flat 2D images with no really physical understanding of what these images are in the real world. So I'd be interested in hearing, are we, of course, from in the perspective of, in comparison to 30 years ago, we do expose networks to a lot of data, but is this a lot in comparison to humans?
Yeah, that's a bit of the point of self-supervised learning, because you can use unlabeled data to train the system, basically raw video, right? I mean, you can't use yet raw video. Right now it's, you know, distorted images with a distortion model, but eventually there'll be some success in sort of using self-supervised learning from video. And then hopefully, you know, the system trains from this will understand the concept of, you know, three-dimensionality of the world, the fact that there are objects that can move independently, the fact that those objects, if they are inanimate, follow predictable trajectories, etc. In fact, you know, the chart I showed briefly in my talk from Emmanuel Dupuy shows that human children learn about gravity around the age of 9 months, between 8 and 9 months. So before that, you show a 6-month-old baby a trick, you know, a scenario in which an object appears to float in the air and they don't seem surprised. But after 9 months, they're really surprised because they figured out that an object that is not supported is supposed to fall. So it takes them that long to figure out that there is such a thing as gravity. And, you know, 8 months is before they start walking. You know, it's after they start, it's after they can grab objects and throw them away. So I don't know if you have 8-month-old babies, you know, but put them on their high chair, you put some objects on them, whether it's food or not, what they'll do is throw them on the ground and look at them. And it's because, you know, they're experimenting with gravity.
They do it over and over, and it's really terrible when you're a parent. We have 3 kids, and I remember the phase when they throw things down. It really takes forever until they realize that, yes, they drop every time, and yes, the glass is broken every time.
It's causal intervention to do an experiment that verifies the validity of gravity. You know, it's basically, it's a small physics experiment that they do. So, but they learn very basic concepts earlier, right? So the basic concepts that the world is 3-dimensional, you can imagine you can learn this spontaneously because it's the best explanation for how your view of the world changes when you move your head, or when you have 2 different views of the world from your 2 different eyes, right? From your 2 eyes. It's just the most logical explanation for, like, you know, every pixel in the world has a depth, right? That's the best way to explain how things change when you move your head. And once you have that, then you have objects that occlude others, right? So now you can learn the notion of object, the notion of object permanence, the fact that objects that disappear behind another one are still, you know, are still there, and then things like that. And that happens, all of this happens in the first 2 months, essentially. For some people, actually, some psychologists say it's innate, but it's very debated. It's highly debated.
And I was mentioning earlier this example of the tennis ball and humans being able to catch the tennis ball. I remember as a kid, I spent a lot of time playing with tennis and soccer and everything. And I was struck at some point to realize that if someone throws you a tennis ball, you can sometimes catch it with your eyes closed. So, you know, even just having fractions of the trajectory is enough to predict where and when it's going to impact, right? And when I noticed that, I was really struck and thought, wow, what's going on in the brain that allows us to do these kinds of things? And I also realized, so with my kids, that takes many, many years. You know, my oldest is now 10, the middle one is 7, the little one even smaller. And if you look at how they do catching balls, you see, you know, it takes many years to be able to predict all of this.
You should be careful at throwing balls at your children when their eyes are closed, because you could get hurt. Right?
I want to comment on prior knowledge in Bayesian stuff. Sorry. So there's a long tradition, and it's sort of dominant in the last years, at least in machine learning, that priors in terms of priors and parameter. And that's, of course, a very strong approach and very powerful. But I have prior knowledge about Yann, and it's not about a prior like how he looks like or something. It's about, I know where he works, I know his history, I know his papers, I know some of his ideas. So this type of prior knowledge, I think, could be really important, or should be more, maybe a stronger link between like the sensation-oriented analysis of images, of scenes, and so on, and adding all this background knowledge. And this background knowledge, I think, is where symbolics and other things come in. And that's also a very important type of prior knowledge, which sort of seems to be a little bit neglected in the discussion on prior knowledge and integrating prior information we are mostly doing in machine learning.
So I think this is, you know, prior knowledge in learning is an important open challenge, obviously. How now that we have all the success of more data-driven approaches like the deep networks, how can we bring a lot of the prior knowledge back into these approaches?
Yeah, but in the sense of adding knowledge, no? I mean, of course, all these other issues are also important, but it's not something just improving some classification system. It's I know that I recognize this person in front of me is Yann, and then I have all this background knowledge to add. And I think that's an important dimension which is not completely captured in our current work, or not enough. I think, see, this is a great link between the classical way of doing AI and the modern way of doing AI, because the modern way is not capturing a lot of these issues, no? Background knowledge, relationship, Munich is in Bavaria, Bavaria is in Europe, Yann lives in New Jersey, whatever, he's an astronomer in his free time. So all this stuff is also a type of prior knowledge, and it might influence our decisions. So it's not irrelevant, it's not just, oh, nice to know. It's something which might influence the way we act, and that's, I think, what it's all about. Now we have to act better. So I want to argue that this is something, some way of integrating the old world with the new world or whatever, which I think is a very interesting challenge. And yeah, I happen to work on that.
Now we have Christian and then Katharina. Christian.
Yeah, so in the current discussion, it's interesting to see that we are not talking much about humans, only as an example. So we just say, oh, we would want to be more human-like. Isn't it also interesting for the next steps in machine learning to do what in robotics is always natural, namely manipulation, and you want to interact with your environment, but now also assuming that there are humans, and maybe also interactions among human and algorithms, algorithms and algorithms, humans. I mean, all what I think now in the latest Nature article was called collaborative AI. Is that maybe important to get it done, what we are dreaming of, and moving a bit more out of the standard AI lab or machine learning lab?
Katharina.
first, I really agree, Christian, that we should embed our work into all kinds of actions, actions on the world, or collaborations with other people, or communication. So these are all actions, and these actions might follow from our, they might follow as a forward inference from our models. And on the other hand, they can also be kind of a self-supervised modeling, such that I do an experiment with the world, acting on the world, but also that I create a communication demand and do some communication with others in order to learn, such that this also can be a self-supervised modeling, that I do communicate and that I do some kind of embedding of my knowledge. That's now answering to Volker, that I want to do my models behave in the world, I want them to be embedded in the world, and I want them to be communicative or interactive.
Yeah, when it comes to trying to mimic humans or getting more similarity to humans, one thing to note is obviously that humans have many senses, right? The vision, the sound, but also the tactile senses, the proprioception, ego motion senses. You know, there's so many senses that humans have, and how to integrate all of this sensory information into learning-based approaches, I guess, is something that to some extent people in robotics are looking into. But I think at that point we suffer a little bit from the fact that researchers tend to work in separate communities. Vision people work on vision, NLP people work on language, and you know, getting all this sensory information together is I think also an important challenge, because I think what humans learn is also relationships between the different senses. You know, when the glass falls, what sound do I hear? And so often I infer the properties of the world, not just from one sense, but from many senses in parallel. And I think it's the interplay of multiple senses that gives me all the information about the world around me.
Just want to say that the problem with having many sensors and the problem of robotics is a big investment, having an actual machine that moves in the world and that can break and everything, and that can break things. It makes, and it makes, I think, I mean, again, I think Nicolas would be, Vincent would be better than me at saying that, but it makes reproducibility, for example, you know, and Daniel, you know that as well, right? Reproducibility in robotics, for example, remains a real tough challenge. It's very hard to compare experiments and things like that. So. I think it's more complicated work as well as a heavy entry price too. So
I think we can take this as a summary, Jean, that there is a lot of challenges that remain open, and you know, lots of difficult things ahead of us. But I think the discussion was very exciting, and I thank all of you for participating on behalf of Jean and myself. Thank you so much for joining this lively discussion. And I think with that, we'll close today's event and we'll reconvene tomorrow at 9 o'clock. Thank you so much, everyone. It's been
maybe I can still add something. So thank you for organizing, and looking forward to tomorrow. But it's also you who has organized it. So thank you.
Sure. It's my great pleasure. Thanks, everyone.
Thank you, Daniel.
Take care.
Bye.
See you
Bye-bye.
tomorrow.